Welcome back everyone to this lecture on the union and union all set operators. Let's get straight into it. The union operator combines the output of two or more select statements into a single set of rows. Union also removes any duplicate rows that might result in the combined output. The syntax of a union looks like the following. So in this example, we have a select statement where we are selecting two columns from a table. Then we write the keyword union followed by a second select statement. Rules for set operators applies to union, union all, intersect, and except set operators. There are two main rules we need to follow when using any of these set operators. These are: each select statement must return the same number of columns. In our syntax example, we can see that this rule has been followed, as each select statement is selecting exactly two columns. The second rule is that the corresponding columns in each select statement must have data types that belong to the same data type group. Data type group just means that the data types are identical or similar enough so that the SQL engine is able to do an automatic data type conversion to make them the same. So for example, if the first column in the first select statement was an integer number data type, and the corresponding column, which is the first column in the second select statement, was a date data type, then we would likely get an error message as number and date data types are incompatible with each other. Okay, let's go for an example. On the left, we have a table called customers, and on the right, we have a table called Canadian subscribers. Let's now union together the rows from both tables so that we get everyone's name and email address. In our first select statement, we have select first name, comma last name, comma email from customers. Then we have the keyword union, and in our second select statement, we have select first name, comma last name, comma email underscore address from Canadian underscore subscribers. So we made sure that the columns are in the same order in each select statement, and we have the same number of columns in each select statement as well. The data types of the corresponding columns are all compatible, as they are all variable character data type columns. This query gives the following result. First, note that the column names in the query result are the names specified in the first select statement. For example, we have a column called email, rather than the corresponding column name in the second select statement, which was email address. So this is going to be the case for all set operators. With all set operators, it's always going to take the column names from the first select statement. Also note that a duplicate has been removed. This is for the customer Edward Ford. So we can see that Edward Ford, who has an email address of ef123@gmail.com, appears in both the input tables. In the context of this query, the duplicate is removed, and therefore we just have one row for Edward Ford in the query result. Notice also that we have two customers called Paul Roberts in the query result. However, this is not a duplicate row, because not all the values are the same across each of these two rows. For instance, these two rows have different email addresses. Therefore, it is likely that these are two different people who happen to have the same name. Okay. So with this query, as it is written at the moment, we might get rows returned in any order. However, if we want to order the rows, we can do so by adding an order by clause. Let's order the rows by email in ascending order. So notice that when we use order by, then we need to order by a column name as given in the first select statement. So in this case, we order by the column called email. We do not order by the column called email address, as it was specified in the second select statement. Okay. Let's say we want to add the column called country from the customers table to our query result. However, if we try to add this column, we will get an error because we now have a different number of columns in the two select statements. The first select statement is selecting 4 columns, and the second select statement is selecting 3 columns. In this case, one workaround is that we can add an expression to the second select statement so that we have an equal number of column expressions in each select statement. For example, so here we are assuming that all the people in the Canadian subscribers table are from Canada. Therefore, we add on the expression Canada as country. So we've specified the text string Canada in single quotes as country. And this expression is going to add the text string Canada for each row from the Canadian subscribers table and put it into a expression called country. This query gives the following result. Okay, let's go back to revisit our first query. As mentioned earlier, union removes duplicates. So in this case, the duplicate for Edward Ford was removed from the query result. Therefore, we just get Edward on one row in the query result. If we want to keep all rows, including duplicates, then we can use the union all set operator. Let's do that. So now we have the duplicate row included in the query result. Generally speaking, you will want to use union rather than union all, as most of the time you will not want duplicate rows in your query result. However, if you know that the data you are combining is guaranteed to never have duplicates, then you might want to use union all. This is because union all is a bit faster than union, because it does not have to check for duplicates and remove them. Hello and welcome to the set operator challenges. Let's go to the first challenge. So for the first challenge, you are to return all rows from both the bird.california sightings table and the bird.arizona sightings table. Use column names from the bird.california sightings table. So coming up is the hint. So the hint for this one is to use the union all operator. Alright, moving to the second challenge. Return all unique species as identified by the scientific name column for species which have been cited in either California or Arizona. Use column names from the bird.california sightings table. And for the hint, use the union operator. Alright, let's move to the third challenge. Return all unique combinations of species, which is the scientific name, and the state name. The state name will need to be added on as a new expression which gives the applicable state name. Use column names from the bird.california sightings table. Also, order by state name and then by scientific name in ascending order. Alright, so coming up is the hint. Use the union operator. Moving to the fourth challenge. Return all rows from all the bird sightings tables, i.e. Arizona, California, and Florida. Use column names from the bird.california sightings table. Coming up is the hint. Use nulls for the Florida sightings common name column, as this column is not in Florida sightings. However, it does exist in the other two sightings tables. Include state name as a column expression. Alright, so have a go doing those 4 challenges, and in the next video we will be going through the solutions. Okay, welcome back. So now let's go through the solutions to the set operator challenges. So for the first challenge, you were to return all rows from both the bird.california sightings table and the bird.arizona sightings table, and you were to use column names from the bird.california sightings table. So first of all, because we want to return all rows from both these tables, we want to use the union all operator. So we're going to select columns from the first table, union all And then we have our second select statement where we are selecting the corresponding columns from the second table. Because we want to use the column names from the California sightings table, this means that we select from the California sightings table first. And to get the column names, we can have a look in the navigator here under the bird schema, under tables, and then California sightings columns. So here are our columns here, and now let's open up Arizona sightings columns. And notice that for Arizona sightings, we have a column name called sighting location, and this corresponds to the California sightings column, which has a different name, which is location of sighting. So other than that, all the other columns have the same name, and they also have compatible data types. So we have sighting ID, common name, etc. We can see the data types of each column by clicking on the column, and then down here it'll tell us the data type. So sighting ID is an int data type in the California sightings table, and sighting ID in the Arizona sightings table is also an int data type. Another way is to right click on the table name, click on table inspector, and then click on columns, and we can see the data types here as well. Okay, so let's highlight that query and execute it. Okay, so we get 10 rows returned, and these are all the species sightings from the California and Arizona sightings tables. Alright, let's now move to the second challenge. So for the second challenge, you were to return unique species as identified by the scientific name, which have been cited in either California or Arizona. And again, you were to use column names from the bird.california sightings table. So now we're just going to be selecting just the scientific name from each table. And so we have select scientific name from bird.california sightings. And also we're going to be using the union operator, and we're using the union operator instead of union all because union will remove duplicate rows. So we have union select scientific name from bird.arizona sightings. So because we're only selecting the scientific name from each table, each row is just the scientific name, so we will get a set returned of unique scientific name values. Okay, so let's highlight that and execute it. Okay, so we get 8 rows returned, and these are all the unique species that have been cited at either California or Arizona. Alright, let's now move to the third challenge. Okay, so for the third challenge, you were to return all unique combinations of species as given by the scientific name, and you were to add on the state name as a column expression. So because we want unique combinations of species and state name, we need to use the union operator to ensure that there are no duplicate rows in the set that gets returned. So in our first select statement, we have select scientific name, comma, and then we've got the text string California in single quotes, and we are aliasing this to the name state_name, and then we're selecting from the bird.california sightings table. We have the keyword union, and in our second select statement, we have select scientific name, so it's in the same order as up here, and then we have comma, and we're going to have the state name. We don't need to include the as state name for the second select statement, although if we did, the query would still work okay. But in this case, I've just written Arizona in single quotes from the bird.arizona sightings table. And then finally, we can order by state name and then scientific name. The order by expression happens conceptually after the select statement, and this allows us to order by state name. So we order by state name in ascending order, ascending is the default, therefore we don't need to include it. We have comma, then order by scientific name within each state. Okay, so let's highlight all that and execute it. Okay, so now notice that we get 9 rows returned, whereas previously we got 8 rows returned. And this is due to a species which has been cited in both California and Arizona. And it's this species here, which is Calopepla gambili. So this species has been cited in Arizona, and if we look down here, it has also been cited in California. So the union operator removes duplicates, but in this case, this is not a duplicate row because it has been cited in both California and Arizona. So in the previous example, when we were just selecting scientific name, we got a unique set of scientific names. Now in this example, we're doing scientific name and state name. So we still get unique rows, but we're getting unique combinations of values. So when we combine the two columns together, then they are unique. Alright, let's now move to the fourth challenge. So for the fourth challenge, you were to return all rows from all the bird sightings tables, i.e. the Arizona, California, and Florida sightings tables. And just as in the previous examples, you were to select the column names from the bird.california sightings tables. Also, you were to include the state name as a column expression. Okay, so we're going to select our column names from bird.california sightings table. Then we use union all, select our columns from the bird.arizona sightings table. Union all, select columns from Florida sightings. So the key thing is that we want to make sure that all the corresponding columns are in the same order and that they have compatible data types. Now notice that the Florida sightings table does not have a common name column. So if we have a look at Florida sightings and columns, so we only have 4 columns in this table, whereas the other tables like Arizona have 5 columns because they also have a common name, but in Florida we don't have a species common name column. So we can get around this by going null as common name. So this will set nulls for all rows from Florida sightings for a new expression called common name. Okay, so let's just click in the query and execute it. Okay, so we get 17 rows returned, and that is all the rows from all the sightings tables. And one other thing to mention is that the sighting date column is now of the date time data type. So we have the date and a time component. And this is because in the Florida sightings table, the sighting date time column was of date time. So if we scroll down here, we will see for Florida, we have some time components as well. Alright, so that's it for the solutions to the set operator challenges. See you next time. Hello and welcome back. In this tutorial, we will be looking at self-contained subqueries. Okay, let's get started. Here we have a table of products. Let's say we want to write a query to return the product details for the product or products which have the highest price. One way we could do this is we could first write a query to get the max price. So we have select max price from products, and this gives us the following query result. So we get the value 95. Looking at the products table, we can visually see that product ID 6 has a price equal to the maximum price of $95. To actually get the row for that product, we could then write a query to select columns from products where price equals 95. Let's do that. So this query now returns what we wanted, which is the product or products with the highest price. However, we had to write 2 separate queries to get to the result. So this is not a very dynamic process. A better way to get the product details of the product or products which have the highest price is to use a subquery. Let's show that. Okay, so now we have select columns from products where price equals, and then we specify our original query in parentheses. The select statement in the parentheses is what is called a subquery. A subquery is simply a query contained within another query. In this case, this is an example of a self-contained subquery. This just means that the subquery is not dependent on the outer query. If we wanted to, we could just highlight the subquery and run it independently. This is also a single row subquery because the subquery only returns one row. In other words, select max price from products is just going to return one value. Single row subqueries are also called scalar subqueries. In the outer query, we have the where clause, where price equals the value returned by the subquery. This query returns the result we wanted, which is any products which have a price equal to the highest price in the products table. Let's now go for another example. So again, we have our table of products, and now we are also interested in the order details table. Let's say we wanted to write a query to return all products from the products table, where the product ID was also in the order details table. We can do that by using a multiple row subquery. For example, so now we are selecting columns from products where the product ID is in, and then we have our subquery in parentheses. And our subquery is now going to return multiple rows. And that's why we've used the n operator rather than equals. This is also a self-contained subquery. If we were to run just the subquery, then we would get the following result. So the subquery returns multiple rows. In this case, it's returning all the product IDs from the order details table. The where clause in the outer query then applies a filter to keep only product IDs that are in the subquery. Okay, so this query gives the following result. So typically the n keyword is used for multiple row subqueries. We cannot use the equals operator for subqueries that return multiple rows. This is because equals is used to compare one item to one other item. Also note that, at least conceptually, SQL evaluates what is in parentheses first. So it first evaluates the subquery, and then the output of the subquery is returned and used by the outer query. Hello everyone. In this tutorial, we are going to be looking at correlated subqueries. Correlated subqueries are a type of subquery where the subquery references a column from the table in the outer query. Because a correlated subquery depends on the outer query for its values, this means that you cannot simply run the subquery independently. This means that correlated subqueries can be a bit trickier to work with as compared to simpler self-contained subqueries. A correlated subquery may be evaluated once for each row processed by the outer query. This can mean that correlated subqueries are slow to run. However, this is not always the case. Depending on the situation and the database engine you are using, the database engine might be able to optimize the query performance. This means that a correlated subquery might not necessarily be evaluated once for each row in the outer query. However, it is helpful to think about this row by row evaluation when learning correlated subqueries. Okay, that is enough background information. Let's dive into an example. Here we have a table of products, and let's say we have the following objective. Return all products which have the highest price for their product category. We can do that by writing the following query. In this query, we are using a correlated subquery to return the maximum price out of the products where the category is equal to the category in the outer query. Note that both the outer query and the subquery refer to different instances of the same table, i.e. the products table. So in the outer query, the products table is aliased to P1. And in the subquery, the same products table has been aliased to P2. This is necessary to do because then we can relate the category column from the subquery to the category column from the outer query. And we do that in the where clause of the subquery. So in the where clause, we have where p2.category equals p1.category, and p1.category is referencing the outer query category column. So for instance, when the outer query has a value of commodity for the category column, then the subquery will return the maximum price out of all products where the category is commodity. Let's go through how each row is processed at a conceptual level. If we take the first row, the category column equals commodity. To show how this query is being processed, let's sub in the category value into the where clause of the subquery. So for row 1, the category value is commodity. So p1.category equals commodity for this row. When the subquery processes this row, it is going to return the maximum price where category equals commodity. If we look at all the rows where category equals commodity, we can see that the highest price for this category is $51. Row 1 has a price of $51, so it meets the condition as specified in the where clause of the outer query, i.e. where price equals the max price for the commodity category. So this row, row 1, will be included in the query result. Now we move on to the next row, row 2. So row 2 belongs to the category niche. So now the where clause in the subquery is calculating the max price where category equals niche. If we look at the rows where category equals niche, the highest price for this category is $95. Because row 2 does not have a price equal to the maximum price for its category, this means that this row evaluates to false, and therefore it is not included in the query result. So we continue on like this by having the subquery calculate the maximum price for each category as given by the row being evaluated in the outer query. Okay, so we get 4 rows in the final query result, and these are all the products which have a price equal to the maximum price in their respective product categories. Now, in this case, there are actually a couple of different ways we could have written this query. For instance, we could have written this query as a join to a self-contained subquery. Let's quickly go through that. So now we have a self-contained subquery. This subquery has been aliased to P2. And this subquery is grouping the products by category and calculating the max price for each category, and we are calling this max cat price. So the subquery table looks like this. So this subquery is then inner joined to the products table on the category and where the product price equals the maximum category price. This query returns the same result as the correlated subquery we did before. Later on, we will look at how we can achieve the same result, but by using an analytic window function. Welcome back everyone. In this tutorial, we will be looking at the exists operator. Okay, let's get started. So again, we have our table of products, and we are also interested in the order details table. Let's say we had the following objective. Return all products that have been ordered as given in the order details table. In other words, return products where the product ID exists in the order details table. We can write this query by using the exists operator. The exists operator accepts a subquery as an input and returns either true or false. If the subquery returns at least one row, then exists will evaluate to true. If no rows are returned by the subquery, then exists returns false. The database ignores the select list of the subquery because it only cares about if the subquery returns any rows or not. Therefore, it does not matter what we specify in the select list of the subquery. In this case, I've just put select asterisk. The exists operator is typically used in conjunction with a correlated subquery. For example, this query here is a correlated subquery. We are selecting columns from products where the product ID exists, and then we have our correlated subquery in parentheses here. And we have select star from order details, which we are aliasing to O, where O.productID equals P.productID. P.productID we get from the outer query. So this is our correlation. Recall that on a conceptual level, a correlated subquery gets evaluated once for each row processed by the outer query. Therefore, each row in the outer query will evaluate to either true or false, as given by the existence or non-existence of the product's product ID in the order details table. Okay, let's go through and see how each row is processed on a conceptual level. If we take the first row, the product ID equals 1. To show how this query is processing each row, let's sub the product ID value into the where clause of the subquery. So when processing row 1, the exists evaluates to true because we have at least one row in the order details table where product ID equals 1. Therefore, this row gets included in the query result. Each row in the products table is then evaluated in this way. Okay, so we get 4 rows in the final query result, and these are all the products which have matching product IDs in the order details table. Another way of getting this same result would be to use the in operator, and this is what we did in the tutorial on self-contained subqueries. So if we look at both methods, so the top method is where we're using exists, and the bottom query is where we're getting the same result but using the in operator. Which query is better performance-wise? Well, it depends. For example, the SQL engine might create an identical execution plan for in as it does for exists. If that happens, then there will be no difference in query performance. As a rule of thumb, exists is faster than in when the subquery result is very large. Conversely, the in operator tends to be faster when the subquery is very small. Welcome back everyone. In this tutorial, we will be introducing the topic of window functions. SQL window functions were officially introduced into the SQL standard back in 2003. However, even though they have been around for a while, a lot of people still don't know about them. I have come across many situations where someone has written some very complex SQL queries with many joins and subqueries which have aggregations in them, when the same result could have been achieved in a much simpler way by using a window function. Okay, let's get started. There are three broad types of functions in SQL. These are single row functions and operations. These are functions which operate on a single row at a time and return one output per row. Then we have aggregate functions. These operate on multiple rows at a time and return a single value per group of rows. Then we have what this tutorial is all about, which is window functions. Window functions operate on multiple rows at a time, but return one output per row. Okay, so let's look at an example. Here we have our table of products. And note that I have changed the price for product ID 7 to $51. We have a total of 3 products in the commodity category. And now 2 of these products have a joint equal highest price of $51. Okay, with that in mind, let's say we have the following objective. Return all products which have the highest price for their product category. Previously, we saw how we could achieve this by using a correlated subquery. This gives us the result we wanted. We also saw how we could get the same result by using a join to a self-contained subquery, for example. So here we are doing the aggregation in the subquery and then joining back onto the products table to get the products with the highest price in each category. Okay, so now I'm going to show you how to write this query by using a window function. And in this case, we will be using the rank window function. Let's go through that. So first, we add the window function to the select clause. And this query now gives the following result. We have added the rank window function and we have aliased this expression to the letters R and K. I've called it R and K rather than rank because rank is a keyword in SQL and it's best practice not to name expressions the same as SQL keywords. Okay, so what is this doing? Well, the rank window function determines the rank of a value in a group of values based on the order by expression as specified in the over clause. So in this function we have the keyword rank followed by an open parenthesis, then close parentheses, and then we write the keyword over, and the over clause is used to define the set of rows for the function to work over. So within the over clause, we have the keywords partition by, and in this case we are partitioning the rows by the category column. So in the first partition, we have all the rows with a category of commodity. In the second partition, we have the rows with the category value of convenience. Then we have niche. And finally the unassigned category, which just has one row in its respective partition. Okay. After the partition by, we then have an order by expression, and we are ordering by price in descending order. This means that we are starting with the highest price. So the highest price product or products will get assigned a rank value of 1 within each partition. The rankings are reset for each partition, i.e. group of rows. If 2 products in a particular category have the same price, then they will get assigned the same rank value. We can see that this is the case for product IDs 1 and 7, which are both in the commodity category, and these both have a price of $51, which is the highest price for the commodity category, and they both get a rank value of 1. Now all we need to do to get only the products which have the highest price for their respective product categories is to filter the data by selecting only rows which have a rank value of 1. So let's show that. This gives the result we wanted. To summarize, we calculated the rank for each row in the subquery, and then in the outer query we have the where clause, where rank, RNK, equals 1, to keep just the highest priced products in each partition. The reason why we needed to put the window function in a subquery is because of the logical processing order. Recall that what is in the from clause gets evaluated first, and then after that the where clause gets evaluated. So we determined the rank values in the from clause in the subquery, and then after that we have the rank values in a column available to us in the where clause in the outer query, where we then apply the filter to keep only rank values equal to 1. Personally, I find this solution much easier to read, especially compared to using a correlated subquery or a join to a subquery. All we had to do in this case was simply to use a window function, put it in a subquery, and then filter it to get the result we wanted. Welcome back everyone. In this lecture, we will be going through common table expressions, which is sometimes called CTEs for short. A common table expression is similar to a derived table. Recall that a derived table is simply the tabular result from a subquery that is given a name. Common table expressions are similar to derived tables in that they are both named subqueries that are only visible to the statement in which they are defined. Okay, let's look at the syntax for a common table expression. So to do a CTE, we first write the keyword with. Then we give the CTE a name. We have the as keyword, and then in parentheses here, we define our inner query, so our select statement. So this is our subquery here. And then after the parentheses, we then have the outer query. So this is our outer select statement, and this is where we typically will select from the common table expression. Okay, let's look at a derived table query next to an equivalent common table expression. So in the top box here, we have a derived table query. And this query is from a previous lecture where we used a window function to rank products within each category by price. So we put this query into a subquery. So the subquery is in bold here, and we've aliased this subquery to the letter S. So the name of this subquery is S. And then in the outer query, so this is our outer query here, we are selecting the columns from the derived table where the rank is equal to 1. This gives us the highest price product or products within each category. So notice that the subquery appears in the from clause of the outer query. So this is the structure that we are used to using. Now if we looked at how we would write the same query, but by using a common table expression, in this bottom box here, we get the same result, but by using a common table expression. A common table expression always starts with the with keyword, and then we name the CTE. And in this case, we're just naming it to the letter S. Then we have the as keyword, and in parentheses, we define the subquery. So with a common table expression, we define the subquery first. The subquery here is then followed by the outer query, and in this case we are selecting the columns from the common table expression S where the rank equals 1. So you can see that the syntax for a CTE provides a more modular approach, which many people find easier to understand. We can also specify multiple common table expressions in the same query. Let's go for an example of that. So here we have two tables. We have a table of account contacts and we have a table of orders. So each account has a contact person and each order is placed by an account. Let's say we had the following task. Return account contacts for contacts who have not been contacted since 1st of January 2020 and have also not made any orders since 1st of January 2020. Let's look at how we could write this query by using two common table expressions. So in this query on the right here, we are first defining a common table expression called not recently contacted. So we have with keyword followed by the CTE name, which I've named not recently contacted, the as keyword, then we have the subquery below. So for this subquery, we are selecting some columns from the account contacts table where the last contacted column is less than 2020 January the 1st. And then because we are specifying more than one common table expression, after the first one, we put a comma after the parenthesis, and then we can specify the second common table expression, which I've just called old orders. So notice that we only need to write the with keyword one time, so we do not repeat the with keyword when specifying the next common table expression. All we need to do is put a comma between them. So the second CTE is called old orders, and I'm selecting some columns from the orders table where the order date is less than 2020 January the 1st. Then finally we have the outer query. So notice that there is no comma between the parentheses of the last common table expression and the outer query, so the select statement down here. So the outer query in this case is selecting some columns from the not recently contacted common table expression, which we've aliased to NRC. We are then using where exists to only return account IDs that exist in the old orders common table expression. So we have where exists, and then in our correlated subquery, we are selecting from old orders and matching on the account IDs between the common table expressions. So we are only returning account IDs that exist in the old orders common table expression. This query returns one row, which is for contact James Verco, who was last contacted in 2019, and is the contact for account 103. And if we look at account 103, this has an old order which was also placed in 2019. There are other ways that this query could have been written. However, this is just an example of how we can specify multiple common table expressions within one query. Alright, that's it for this lecture. See you in the next one. Hello and welcome to this lecture on avoiding the not-in trap. First, we're going to cover what the not-in trap is, and then we're going to go through a few different ways that we can avoid it. Alright, let's get straight into an example. So in this example, we have two tables, a table for departments and a table for employees. These tables can be linked based on the department ID columns in each table. For example, employee Vera Hill is in department ID 101, and if we look at the departments table, we can see that department ID 101 is the accounting department. Now let's say we have been given the following task. Write a query to give all the departments that currently have no employees. Just by looking at the tables, we can see that the result we want is going to be department IDs 103 and 104 because currently they have no employees in them. This is because if we look across at the employees table, we can see that we only have employees for departments 101 and 102. And we have one employee, Joanna Gomez, who has a null for department ID and therefore is not assigned to any department. Okay, one way we can write this query is by using the not in operator. However, we need to be careful to avoid what some people refer to as the not in trap. So first let's write the incorrect query just to demonstrate the not in trap. So here we are selecting all columns from the departments table where department ID is not in, and then we have in a subquery here, select department ID from employees. However, this will not give us what we want, and instead it will actually return no rows from the departments table. This query has not returned any rows because we have a null in the department ID column of the employees table, and that is for employee Joanna Gomez. So this null here is basically what stuffs up the query. If there were no nulls in the department ID column in the employees table, then we would actually get the correct result, but because this column currently allows nulls, then using not in will not return us any rows. The reason for this is that the not in condition is actually doing a series of AND operations. So in this case, it is equivalent to doing this. Select all columns from departments where department ID does not equal 101 and department ID does not equal 102 and department ID does not equal null. So it is this last condition here which causes the problem. Department ID not equal to null. This is because no row will ever meet this condition. Remember, we should not use equal to null or not equal to null because a null is not equal to anything else, including another null. Instead, we need to have is null or is not null. So in this case, what we want is department ID is not null, but that is not what the not in condition gives us. Okay, so let's go back to our starting point again. So how can we write a query to get the right result? Well, one way is to simply add a where clause to the subquery in order to exclude the nulls. For example, now in the query we have select all columns from departments where department ID not in, and then our subquery we have select department ID from employees where department ID is not null. So we are making sure that there are no nulls returned by the subquery, and this gives us the result we wanted, which are departments 103 and 104. Another way we could get the departments that don't have any employees in them is by using not exists instead of not in. Let's now take a look at that. So this query also returns the correct result, i.e. departments 103 and 104. The not exists condition does the opposite of exists, and it evaluates to true if the condition in the subquery is not met for at least one row. The subquery, in parentheses here, checks if the employee's department ID matches the department ID, which it gets from the outer query. Matched rows evaluate to false because we are using not exists. The unmatched rows get evaluated to true and therefore returned by this query. Note that if we were using exists rather than not exists, then the reverse would be true and we would instead get the matched rows returned. Recall that exists and not exists are typically used in conjunction with a correlated subquery, and this is the case here as we have the where clause in the subquery, which is the e.department ID equals d.department ID, and d.department ID is a reference to the outer query, and therefore this is a correlated subquery. Okay, so this query returns the unmatched rows, which in this case are the sales department and the IT department. So this is another way of returning departments that don't have any employees. Okay, let's go back to a clean slate. Okay, let's now look at one more way that we can write this query, and that is by using an outer join. So let's take a look at that. So this query gives us the result we wanted, departments 103 and 104, as these currently have no employees. If we look at this query, it is saying select all columns from the departments table, which we're aliasing to the letter D. And then we're going to be doing a left outer join to the employees table. Recall that the outer keyword is optional, and in this case I've just written left join. And we are joining on the department ID in each table. Then we keep only the rows where the employees department ID is null. For illustration and to show how this query works, I'm just going to show a couple of the attributes from each of the tables. Okay, so conceptually, first what happens is the outer join of departments to employees. We're using a left outer join, and so this means we're going to return all the rows from the left hand side table, regardless of whether there are matching rows in the right hand side table. The departments table is specified first in the from clause, and therefore departments is our left hand table. And this means we preserve all rows from the departments table, regardless of whether or not there are matching rows in the employees table. Notice that at this stage, we are just doing the outer join. And also notice in this case, I'm just specifying the department name from the departments table and the department ID from the employees table. Okay, with that in mind, let's now take a look at the result of this query. So the query result is given on the right here, and so we have the accounting department, department ID 101, and this joins to 2 records in the employees table. Then we have the marketing department, which is 102. This also has 2 employees. And then we've got departments 103, the sales department, 104, IT. And these 2 departments have no matches in employees. However, they still get returned in the query result. And this is because we are preserving all rows from the left-hand side table, which is the departments table. But notice that they get nulls as placeholders for any attributes from the employees table, such as the department ID. So we get 2 nulls for the unmatched records. So all we have to do now is add on a where clause to keep only rows where the employee's department ID is null. So now after adding on the where condition, where e.department ID is null, we get the result we wanted, which was departments that currently have no employees. It is important that we specify e.department ID is null in the where clause, because table E is our employees table, which is our right hand side table. And when the department ID from the employees table is null, that means that the row is unmatched. As an aside, notice that we have an employee who has not been assigned to a department, and that is employee number 5. So they have a null for the department ID in the employees table. I've grayed out this row as it is not included in the query. Alright, that's it for this lecture, and I'll see you in the next one. Hello and welcome to the subquery challenges. Before going through these challenges, I just want to mention that some of these challenges involve completing the same task but in different ways. The reason for this is so that you can become proficient at writing SQL in different forms. This is particularly useful if you have to check or rewrite some SQL code that someone else has written. And just a warning that some of these challenges are fairly hard, so you might need to go back and watch some of the previous videos, or even have a quick look at the solution SQL file attached to the next video. Okay, with that aside, let's look at the first challenge. Return the following columns for the cheapest product or products in the OES.products table: product ID, product name, list price, and category ID. Coming up is the hint. Use the min aggregate function in a self-contained subquery in the where clause. Okay, moving to the second challenge. Use a correlated subquery to return the following columns for the cheapest product or products in each product category as given by the product ID column. So return the same columns as before: product ID, product name, list price, and category ID. Coming up are the hints. Put the subquery in the where clause. The subquery will also have a where clause which references the category ID in the outer query, hence making it a correlated subquery. Alright, let's move to the next challenge. So for the third challenge, you were to return the same result as challenge 2, i.e. the cheapest product or joint cheapest products in each product category, except this time by using the rank window function in a common table expression. Coming up are the hints. Rank products using the rank window function by price from lowest to highest within each category ID partition. Name this expression price_rank. Also include the same columns as in challenge 2 in the query. Put this query into a common table expression. In the outer query, select the columns where the price rank equals 1. Alright, let's now move to the fourth challenge. So for this one, you're going to repeat or edit the third challenge, except this time include the product category name as given in the OES.product categories table. Coming up is the hint. In the outer query, include a join to the OES.product categories table in order to get the category name. Alright, moving to the next one. The fifth challenge requires a bit of background information. The employee ID column in the OES.orders table gives the employee ID of the salesperson who made the sale. And note that this column, employee ID, in the orders table can sometimes have nulls in it if a sale cannot be credited to a particular employee. Alright, so the challenge is to use the not in operator to return all employees who have never been the salesperson for any customer order. Include the following columns from the HCM.employees table: employee ID, first name, and last name. Coming up are the hints. Use the not in operator in conjunction with a self-contained subquery. However, make sure to exclude nulls from the employee ID column in the OES.orders table as referenced in the subquery. Moving to the next challenge. For the sixth challenge, you are to return the same result as the previous challenge, i.e. all employees who have never been the salesperson for any customer order, except this time use the where not exists operator. Coming up is the hint. Use a correlated subquery to correlate the employee ID in the OES.orders table to the employee ID in the HCM.employees table. Okay, moving to the next challenge. So for the seventh challenge, return unique customers who have ordered the PBX Smartwatch 4. Include the following columns: customer ID, first name, last name, and email. Coming up are the hints. Use the in operator in conjunction with a self-contained subquery. Select customer IDs in the subquery for customers who ordered the PBX Smartwatch 4. Also in the subquery, you need to join the OES.orders table to the OES.orderItems table, and then join this to the OES.products table. Filter OES.products table to return rows where the product name equals PBX Smartwatch 4. So basically, in a subquery, you're going to join up these three tables, filter on where the product name equals PBX Smartwatch 4, and then in the outer query, use the in operator to select only those unique customers who ordered the PBX Smartwatch 4. Alright, so give those 7 challenges a go, and in the next lecture we will go through the solutions. Hello and welcome to the solutions to the subquery challenges lecture. So for the first challenge, you were to return product details for the cheapest product or products using a self-contained subquery. So in the solution here, we have select the columns we wanted from oes.products, where the list price is equal to the output of this self-contained subquery. So to specify the subquery, we put it in parentheses, and then we have another select statement. So this select statement returns one value, which is the minimum list price, i.e. the lowest price in the oes.products table. So it's called a self-contained subquery because we can run this query independently of the outer query. So if we just highlight this and then go up here to the lightning bolt, as we're just executing a selected portion of a script, click on that. So this returns one value, which is 20, and hence we can use the equals operator. So essentially it's going to do where list price equals 20 in this case. Okay, so let's highlight the whole query and execute it. So we get one row returned in this situation, and that is for product ID 67, and it has a price of 20. So this is our cheapest product overall. Alright, let's now move to the second challenge. Okay, so for the second challenge, you were to return product details for the cheapest product or joint cheapest products in each product category by using a correlated subquery. Let's first look at the subquery. So in this subquery here, we have select min list price from oes.products. Then in the where clause, we have where p2.categoryID equals p.categoryID. So this is where the correlation occurs because p.categoryID is from the outer query. So this is going to return the minimum price for each category ID. If we look at the outer query, we are selecting some columns from oes.products, and we're aliasing this instance of the products table to the letter P. Then in the where clause of the outer query, we have where p.listPrice is equal to the minimum list price for each product category ID. Recall that for a correlated subquery, we cannot simply run this subquery independently of the outer query because the subquery is dependent on the outer query. Conceptually, the correlated subquery evaluates each row. In this case, determining if each row has a list price equal to the minimum list price for its respective category ID. Okay, so let's highlight this query and execute it. So we get 9 rows returned. If we just bring this down a bit, this one up. So these are the cheapest products in each category. So for example, in category ID 7, the cheapest product is a LaserJet printer, and it's got a price of $23.25. Okay, let's now move to the third challenge. So for the third challenge, you were to return product details for the cheapest product or products in each product category by using the rank window function in a common table expression. So in this challenge, we're going to be getting the same result as the previous challenge, except this time we're going to be using a different method, which is the rank window function. And we're going to be putting this into a common table expression. So to define a common table expression, we use the with keyword. So we have with, and then we give our common table expression a name. So in this case, I've just called it low price per cat for category. And then we have the keyword as, and then within parentheses, we put the select statement for the common table expression. So we can think of this as our subquery. Okay, so we have select the columns we want, and we're also going to be adding on this window function to calculate the price rank. So the syntax for it is rank, then we have an empty set of parentheses, we have the keyword over, an open parenthesis, then we have the keyword partition by. So what are we wanting to partition by? We are wanting to partition by the category ID. So think of it as separating all the rows into each category ID. Then we do order by, list price, ascending order. Ascending is the default, so we could have left this out if we wanted to. So the lowest list price will get a rank of 1, second lowest a rank of 2, etc. Because we're using the rank window function, if we get two products that happen to have the same price, then they will get the same rank value. Okay, so we're aliasing this to price rank. Okay, so now if we move down to the outer query, we are selecting those same columns, except we don't need to include the price rank, and then we're saying from the common table expression name, where price rank equals 1. So all the products which have a price rank equal to 1, these will be the lowest price items within each category ID, i.e. each product category. Okay, so let's highlight this query and execute it. Okay, so down here we again get 9 rows returned, which is what we wanted, and these are the lowest price products within each category. Okay, let's now move to the fourth challenge. So for the fourth challenge, you are to repeat the third challenge, except this time include the product category name from the OES.productCategories table. So our common table expression remains the same, but in our outer query, we are going to inner join to the product categories table, and we're joining the two tables on the category ID column. And because we're doing a join, often it's a good idea to use aliases. So in this case, I've aliased the common table expression to LPC for lowest price per category. We're joining to the product categories table, which I've aliased to PC. We join the two tables, and then we're selecting most of the columns coming from the common table expression, but we're getting the category name column from the product categories table. Okay, so let's highlight all of that. Execute it, and again we get 9 rows returned, which is what we wanted, and in this case we also have the category name for each category ID. So this is a bit more informative as we can see what category name each category ID refers to. Alright, let's now move to the fifth challenge. So for this challenge, you were to return all employees who have never been the salesperson for any custom order. Use the not in operator. So in the orders table, they have an employee ID column, which indicates the employee ID of the person who made the sale. So basically, we are looking for employee IDs from the employees table that do not exist in the employee ID column of the orders table. And these will be our employees who are not salespeople, and therefore they've never been credited with a sale in the orders table. So if we look at the subquery first, as this is what gets processed, at least on a conceptual level first. So we have select employee ID from orders where employee ID is not null. So it's very important that we include this where clause here, where employee ID is not null, because when using the not in operator, if we had even just one null in our subquery here, then the whole thing would return null. And we saw this in the lecture on avoiding the not in trap. Moving to the outer query, we're just selecting the columns we want from the employees table, where employee ID not in the list of employee IDs returned by the subquery. Okay, so let's highlight that and execute it. So these are all the employees who have never made a sale. Okay, let's now move to the next challenge. So for challenge 6, you were to return all employees who have never been the salesperson for any customer. So it's basically the same as the previous challenge, except this time we are to use the not exists operator. So instead of not in, we have where not exists, and then we have our subquery. And this is actually a correlated subquery. So we have select asterisk, and actually we could have anything in this select clause here as it will be ignored. So often people will put in a 1. However, I often like to just put in an asterisk. Okay, so then we have from orders, aliasing it to just O in this case, where O.employeeID equals E.employeeID. So this is where the correlation takes place, because E.employeeID comes from the outer query. Okay, so let's just highlight all that and execute it. And we get 74 rows returned, which is the same as before. So these are all the employees who have never made a sale. Alright, let's now move to the next challenge. Okay, for the 7th challenge, you are to return unique customers who have ordered the PBX smartwatch 4. And we had to join a few tables to get this one, so it's a bit more complicated. So if we look at the subquery, we are basically selecting the customer ID from orders, joining on to order items, then we join on to products, and then finally we filter where product name equals PBX smartwatch 4. Okay, so first of all, let's just run this self-contained subquery here and have a look at the result. Okay, so we get 36 rows returned, and this gives us a list of customer IDs for customers who have ordered the PBX smartwatch 4. Now potentially we might have the same customer order the PBX smartwatch 4 multiple times in different orders. However, customer ID is unique in the customers table because it is the primary key, so each row in the customers table refers to a unique customer. Therefore, when we select customers from the customers table where customer ID is in the list of customers returned by the subquery, then we will only get a unique set of customers returned from the customers table for those customers who have ordered the PBX smartwatch 4 at least once. Okay, to show that, let's now execute the whole query. So I'll click anywhere in the query and then execute the statement above. Okay, so now we get 28 rows returned. And recall that previously when we ran the subquery we got 36 rows returned. So what this is telling us is that there are some customers who had ordered the PBX smartwatch 4 more than once as part of different orders, but now because we're selecting from the customers table and using it in conjunction with the in operator, we only get a unique set of customers returned, and this is what we have here. So anyway, we get 28 unique customers who have ordered this particular product. Alright, so that's it for this tutorial. See you in the next one. Welcome back. In this lecture, we will be covering concatenation in MySQL. Let's get started. So concatenation is a way to combine character strings end to end. For example, the concatenation of snow and ball is the word snowball. MySQL provides two methods of concatenation. One way is by using the concat function, and the other way is by using the double pipe operator. Note that to use double pipe concatenation in MySQL, you first need to enable the SQL mode called pipes as concat. And on my keyboard, the pipe operator is just above the enter key, and I have to hold shift and then click on the key above the enter key to get one pipe, and then I do this again to get the second pipe. Although that's just my keyboard, and the pipe operator might be in a different location on your keyboard. Okay, let's go through some examples. So here we are selecting some customer details from a table of customers. So we have customer ID, first name, middle name, and last name. So a common task we might want to do is to concatenate the first name and last name together, and in this example we'll do so by using the double pipe operator, and we'll call this new expression full name. So first we need to set the SQL mode to pipes as concat, and we do this by writing set session SQL underscore mode equals, and then within single quotes we write in capitals pipes underscore as underscore concat. After we do this, then MySQL will treat two pipes as a concatenation operator for the remainder of the session that you have open. Okay, so now when we write our query, at the very last one here, we have first name, double pipe, last name as full name. So we can see in the query result, we have this new expression called full name, and we have the concatenation happening here. As you can see, we are missing a space between the first and last name. So what we can do to change this in the query is to concatenate on one space between the first name and the last name columns. So let's show that. So now in our expression we have first name, then we concatenate on a single space. So we just have two quotation marks with a single space between them. Then we have double pipe, so another concatenation, then we concatenate on the last name. Then we alias this whole expression as full name. So when we look at the full name expression up here, this is giving us the result we wanted. So we have Linda space Flynn, Jack space Thomas. Okay, so let's say we also want to include the middle name in our expression. Let's see what happens when we add in middle name. Okay, so we have added in the middle name column and we have a space on either side. So we have first name, concatenate on single space, concatenate on middle name, concatenate on another single space, concatenate on last name. And if we look at the result, we can see that the first row looks okay. So we have Linda, Mary, Flynn. But on the second row, we just have a null. The reason we have a null is because Jack Thomas does not have a middle name. Instead, we just have a null here. So anything plus a null or anything concatenated on with a null always returns a null, and therefore a null is returned for Jack's full name. However, we can circumvent this in our query by applying the coalesce function to the middle name column in order to replace nulls. So let's show that. So in this query, when middle name is null, then we are replacing it with an empty string. So you can see here that in the second argument of the coalesce function, we have just two quotation marks with nothing in between them. So this is an empty string, which is also called a blank. So it's just two quotation marks side by side with nothing between them. So if we look up here at the query result, it looks okay. So now we're getting Jack Thomas. However, if we look at the result more carefully, we notice that there are actually two spaces between the first name and the last name for Jack Thomas. And the reason for this is because we get Jack concatenated on with a single space. He doesn't have a middle name, therefore the coalesce function returns just a blank. And then we get another single space concatenated on here, and then we have last name concatenated on. So in other words, we have Jack space Thomas. Therefore, because Jack does not have a middle name, we end up with two spaces between his first and last names. One way to fix this is by doing the following. So now we have first name concatenate on with this coalesce function here, and within the coalesce function we have a single space, so this is two quotation marks with a single space in between them, concatenated on with the middle name. So all of this is our first argument in the coalesce function, and then we have comma, and for our second argument we just have our empty string again. So if this one evaluates to null, we get a blank returned. Then we have our double pipe, single space, double pipe, last name. So what this coalesce function is doing is it is saying that if the middle name is null, then replace it with an empty string. This is because if middle name is null, then a single space concatenated on with a null still evaluates to null, and therefore we return this empty string. However, if middle name does have a value, then we are going to get a single space concatenated on with middle name. In other words, we get a space added on before the middle name only when middle name has a value. So for example, Linda has a middle name, and therefore we only get an additional space added on before her middle name if she actually has a middle name. For Jack, Jack doesn't have a middle name, therefore this will evaluate to null, so he won't get that extra single space concatenated on. It'll just be the empty string. This gives us the result we wanted, and now we only have a single space between names even if there is a null for middle name. Okay, so another way we can concatenate strings is by using the concat function. Let's now take a look at that. So with the concat function, we just list all the expressions that we want to concatenate in a comma delimited list. And in this case, we need to use the coalesce function to replace nulls with blanks in the middle name column. Note that MySQL's concat function works a bit differently to some other databases. In some other databases, such as SQL Server, the concat function will automatically replace nulls with blanks, but in MySQL that is not the case. In MySQL's concat function, we need to nest in the coalesce function for any columns that allow nulls, such as this middle name column here. Okay, so in this case, we get the same issue occurring as we had before, since we have two spaces for Jack Thomas. However, we can use the same workaround as we did before by using double pipe concatenation between the first space and the middle name. Let's do that. So now we have coalesce, single space, concatenated on with middle name. So this coalesce function is our second argument in the concat function. This means that an extra space only gets concatenated on before the middle name if middle name has a non-null value. Okay, that's it for the lecture. See you next time. Okay, welcome back. In this lecture, we will be covering some commonly used string manipulation functions in MySQL. Let's get started. So the first function we're going to look at is called the instra function, and the instra function returns the index location of the substring in a string. The syntax for this function is the following. So our first argument is string, and this is the string to search. So this is typically where we would pass in a column. And the second argument is the substring, and this is the substring to search for in string, which is the first argument. Okay, let's go for an example. Here we have a table of customers, and in the customer name column, we have the full name of each customer. Let's say we want to write a query to extract only the first name. We can achieve this by using a couple of functions. So we can see that the first name ends once we encounter a single space. And this is because we have first name, space, last name. Okay, so to isolate just the first name, what we're going to do is we're first going to use the instra function to find the position of a character, and in this case the character we are interested in is the single space between the first name and the last name. Okay, so let's add on an instra function as an expression to see how it works. So in the instra function, the first argument is the string to search within. In this case we want to search within the customer name column. And the second argument is the substring we want to find, and in this case we want to find the index position of the first single space within the customer name column. And note that the index starts from 1, so the first character of each customer's name is at index position 1. Okay, so the result of this expression we have named as index position of space. And here it is up here. And so for the customer Adam Lee, we get a value of 5. And this is because the single space occurs at position 5 for this customer. The single space for Marcy Lowe occurs at position 7, and the single space occurs at position 5 for Toya. Now we can combine the instra function with another function called the left function to extract only the characters of the first name. Before we combine these two functions though, let's have a look at the left function separately to understand what it does. So now we have a new expression which we've called first two characters, and we're using the left function to extract the requested number of characters from the customer name column. So the first argument is the string that we want to extract the characters from, which in this case is the customer name column. And in the second argument, we specify the number of characters that we wish to extract from the leftmost character. In this case, we have specified 2, so we extract the first 2 characters for each customer's name. So for Adam, we have AD, Marcy, MA, Toya, TO. So the next step we are going to do is to nest the instra function within this left function. So instead of specifying a static number here for the second argument of the left function, we are instead going to put that instra function in here, which found the position of the first single space for each customer. Let's show that. So this gives us the result we wanted, which was to extract just the first name for each customer. Let's now go through this row by row. Within this expression, what gets computed first is the innermost function, which is the instra function. So when looking at row 1 for Adam Lee, the instra function returns the number 5, which is the position of the first space. However, we don't want to include the actual space at the end of the first name. So what we do is we minus 1 off this result to get the position of the last character in the first name. So hence why we have this minus 1. For the first row, this gives us a value of 4. In turn, this value of 4 gets passed in as the second argument in the left function, which is our outer function. So we get the first 4 characters returned for this particular row, which are ADAM for Adam. Then the same thing happens for the next row. So now for customer Marcy Low, the space occurs at position 7. We minus 1 off it because the single space takes up a character, and then we pass the value of 6 into the left function to get the first 6 characters, giving the first name Marcy. Then we have the last row for Toya Roberts, and we get 4 characters returned for Toya. Okay, let's now remove this first name expression. Now we are going to try and extract the last name for each customer. To do that, we need to combine a couple of functions. And before we go and do that, let's first cover a couple more string functions. Alright, so there is a function called substring, and this function allows us to extract a substring from a string. Let's take a look at an example. So here we have added on an expression which we've called sub, and we are using the substring function to extract part of the customer name. If we look at the syntax for the substring function, the first argument is our string, so we pass in the customer name as our string expression. The second argument is the start position. In this example, we have used a start position of 4. So this is the position that the extraction will start from. So if we look at customer ID 1 for Adam, this means that we start the extraction from the M character, as it is at position 4. And the third argument for the substring function is length. And this is the number of characters to extract from the string. So in our substring function, we have a length of 5. So we are going to start from character 4, and we're going to get the next 5 characters. So we will extract 5 characters in total. So for Adam Lee, we start from position 4, and then we extract 5 characters in total. So we get M space Lee returned. And we do the same thing for the other customers. Okay, so since we want to extract just the last name part, what we can do is we can use the instra function to return the position of the space between the first name and the last name, but this time we will add 1 to it to start from the position of the first letter of the last name. So the instra function will be our start position. And then for the length, this is actually an optional argument. And if we leave this out, then it will return the entire remaining string. Okay, so let's look at the full solution. So here is the full solution here, and to make this a bit easier to understand, let's put a working expression in for what's happening in the second argument of the substring expression. So now the second argument has been added on as a separate expression, which we've just called start position. So for Adam Lee, we can see that the start position is at position 6. This is because the space between Adam and Lee, so the single space here, is at position 5. We add 1 to it to get the position of the first character of the last name, and therefore number 6 is our start position for the substring function. We haven't specified a length in the substring function, and therefore it's just going to extract everything from the L character onwards. For Marcy Low, their space occurred at the 7th position. We add 1 to it to get the start position of the first character of their last name, and then we return everything from that one. Okay, so that's it for the tutorial. I hope you found this useful, and I'll see you in the next one. Hello everyone, and welcome to this tutorial on the case expression. Okay, let's get straight into it. In SQL, the case expression has the functionality of an if-then-else statement. Often people will refer to a SQL statement that includes a case expression as a case statement. However, strictly speaking, the correct term to use is case expression. Okay, let's look at an example. Here we are selecting some columns from a table of customers, and we have each customer's country, and we also have a yes/no column for if they are a club member or not. So let's say we have the following task. Add an expression to the query called customer status. If a customer is from the USA and is a club member, give a value of domestic member for the expression. If from the USA and is not a club member, then give a value domestic non-member. If a customer is not from the USA but is a club member, then their customer status is foreign member. If not from the USA and is not a club member, then foreign non-member. Okay, so let's now look at how we can achieve this by using a case expression. Okay, so here we have added the customer status expression, and if we look at the query, we are selecting some columns from the table, and then we also have our case expression, which we're naming customer status. So first we have the case keyword followed by when, and then after the when, we specify our condition or conditions. So on the first line of the case statement, we have two conditions. The first is where country equals USA, and the second is where we've got club member equals yes. Since we are using the AND operator, this means that both conditions need to be true in order to return a true. We then have then keyword, followed by the value that we want to return if these conditions are met. So if a customer is both from the USA and is a club member, then give them the value domestic member. Moving to the next line, we have another when clause with another predicate in it. And so on this line, we have when country equals USA and club member equals no, then domestic non-member. And on the third line, we have when country does not equal USA and club member equals yes, then foreigner, followed by when country does not equal USA and club member equals no, then foreign non-member. Then we have the else keyword, and in this case we have else unknown. The else is a catch-all, so what this means is that if none of the predicates above return true, then we return the value specified in the else clause. So for example, if we had a customer who had a null for club member, then none of these conditions above would be met, and this would mean that we would return the value specified in the else clause, which we've got the text string unknown. And to finish the case expression, we always need to write the keyword end. And after that, we give the expression a name. So in this case, I've got as customer underscore status. So we're naming it customer status. One important thing to be aware of when writing a case expression is that the when clauses are evaluated in the order that they are written. So we can use this fact to our advantage, and in this case we can get the same result, but by writing the case expression like this. So now in the first two when clauses, we are covering off all the situations involving customers from the USA. Because the when clauses get evaluated in order, this means that once we reach the third and fourth when clauses, we can assume that these customers are not from the USA because we've already dealt with all those customers in the first two conditions, and therefore we only need to test for if they are a club member or not. As you can see, this gives the same result as before. Another thing to know about the case expression is it actually has two forms to it, a simple form and a searched form. The examples we've seen so far are both the search form, which allows us to test multiple columns, as well as use comparison operators such as equals, not equals, etc. Let's now take a look at the simple form of the case expression. So here we have the simple form of the case expression, and notice the syntax difference. Instead of writing case when, we have case, and then after that we specify a column. So we have case country, and then after that we have the when clause or clauses. So this means that the simple form is just testing one input expression, in this case the country column. In this example, we just have when USA, then give the value domestic, else give the value foreign. We end the case expression with the end keyword again, and then we give it a name. So this expression is now being named customer category. Okay, welcome to the case expression challenges. Let's go to the first challenge. So for the first challenge, you are to select the following columns from the OES.products table: product ID, product name, and discontinued. Include a case expression in the select statement called discontinued description. Give this expression the string no when the discontinued column equals 0, and a string of yes when the discontinued column equals 1. In all other cases, give the expression the string of unknown. Alright, let's now look at the hints. So for the hint, you can use either the simple or searched form of the case expression. As a reminder, let's have a look at the syntax for the searched form of the case expression. So given on the left here is the general syntax for the searched form of the case expression, and given on the right is an actual example. So we have the keyword case, and then we have a when clause, so we have when, and then we give a condition. So in this case the condition is color code equals 1, then if this condition is true, return some value. So if color code equals 1, then blue, etc. And at the end we have an else, which is our catch-all, and then we have the keyword end to end the case, and then we can give the expression a name by saying as, and then our expression name. Alright, let's now move to the second challenge. In the second challenge, you are to select the following columns from the OES.products table: product ID, product name, and list price. Include a case expression in the select statement called price_grade. For this expression, if list price is less than 50, then give the string low. If list price is greater than or equal to 50, and list price is less than 250, then give the string medium. If list price is greater than or equal to 250, then give the string value high. In all other cases, give the expression the string of unknown. Coming up are the hints. Use the searched form of the case expression. Also, remember that the when clauses are evaluated in the order they are written. Okay, so moving to the next challenge. Select the following columns from the OES.orders table: order ID, order date, and shipped date. Include a case expression called shipping_status, which determines the difference in days between the order date and the ship date. When this difference is less than or equal to 7, then give the string value shipped within 1 week. If the difference is greater than 7 days, then give the string shipped over a week later. If shipped date is null, then give the string not yet shipped. Okay, let's now look at the hints for this one. Use the timestamp diff function to determine the difference in days between the order date and the shipped date attributes. And just as a reminder, the syntax for the timestamp diff function: first of all we give a unit of time, and then we give the two date expressions that we want to get the difference between. And this is going to return the date expression 2, so this last one here, the third argument, minus date expression 1, which is the second argument. And the unit is our unit of time, and in this case you want to set the unit to day. And when we write the unit of time, we don't put any quotation marks around this keyword here. If you want a refresher on this function, you can reference back to the date and time functions lecture. Okay, let's now move to the next challenge. So in this challenge, you are to repeat the third challenge to derive the shipping status expression, but this time also get the count of orders by the shipping status expression. Alright, let's now look at the hints. Put the query from the third challenge into either a subquery, i.e. a derived table, or a common table expression. In the outer query, use a group by clause to group the rows by the shipping status expression, and use the count function to count the rows in each group. Also include the shipping status in the select clause of the outer query. Okay, so have a go at doing these 4 challenges, and in the next video we will go through the solutions. Alright, welcome to the solutions to the case expression challenges. For the first challenge, you were to add on this new expression called discontinued description. And for this one, our case statement looks like this if we were to use the simple form of the case expression. So with the simple form of the case expression, we just have the keyword case. Then we give the column that we want to case. So in this case, it's discontinued. And then we have our when clauses. So we have when 0, then no. So this means that when the discontinued column is 0, then we want to return a value of no for those rows. And then we've got when 1, then yes. So when discontinued is 1, then we're going to return a value of yes for those rows. Then we have an optional else clause. So in all other cases, we're going to return a value of unknown. So if none of these when clauses evaluates to true, then we're going to return what we specify in the else clause, which was the value unknown. Then we always need the end keyword to end the case statement. So we just write end, and now we can give the case statement a name. So we have as discontinued underscore description. Okay, so let's click in the statement and execute it. Let's just bring this up a bit. Okay, so we have 79 rows returned, and we're selecting some columns from the products table, and we can also see our new expression here, discontinued description. So where it's 0, then we return no, and when it's 1, we return yes for the description. Okay, so another way that we could have written this is by using the search form of the case expression, which is the form that I tend to write my case expressions in, as it's more flexible. Alright, let's have a look at that. Okay, so now we're getting the same as before, but we're using the searched form of the case expression. So now we have case when discontinued equals 0, then no. So basically with the search form, we need to specify the column in each when clause rather than specifying it at the beginning. So for the first condition, we have when discontinued equals 0, then no. So notice that also with the search form, we have our comparison operators. So in this situation, we have the equals operator. So for the second when clause, we have when discontinued equals 1, then yes, else unknown, and as discontinued description. Okay, so let's click in the query, execute it, and we get the same result as before. Alright, let's now move to the next challenge. So for the second challenge, you were to add on a new case expression to give the price grade. And we were to grade the prices into low, medium, or high. So in this situation, we need to use the searched form of the case expression because we need those comparison operators such as less than or greater than. So for the first when clause, we have when list price is less than 50, then low. Then the next when clause, we have when list price less than or equal to 50 and list price is less than 250, then medium, and then we have in our last when clause when list price is greater than or equal to 250, then high, else unknown. Then of course we have our end keyword, and we're calling this price underscore grade. Okay, let's now click in the query and execute it. So we can see we get the result we wanted. So if the price is greater than 250, like this product here, then it gets a price grade of high. And if it's less than 250 but greater than 50, then it's medium, and less than 50, then low. So we could have actually rewritten this case expression and removed this condition here from the second when clause. And let's see why that is the case. So let's scroll down a bit. Okay, so in the simplified approach, we have when list price is less than 50, then low. And then in the second clause, we have when list price is less than 250, then medium. So notice that we did not have to have the extra condition to say that list price is greater than or equal to 50 in this second when clause here. This is because the when clauses get evaluated in order. So all the products that have a price less than 50 have already been evaluated in this first when clause here. Therefore, when we move to the second when clause, it is implied that we are only going to get products that are equal to or greater than 50, and so we only need to specify that list price is less than 250. Then in the next clause, we're setting all products with a list price greater than or equal to 250 to the value high. Okay, so let's click in this query and execute it. And this gives us the same result as before, but because of the way we ordered the conditions, we did not need to include the extra condition up here, which was this one. This is a redundant condition because it has already been covered in the first condition, which gets evaluated first. Okay, so let's now scroll down and move to the third challenge. So in the third challenge, you were to write a case expression called shipping status, which determines the difference in days between the order date and the shipped date. When this difference is less than or equal to 7, then give the string value shipped within 1 week. If the difference is greater than 7 days, then give the string shipped over a week later. If ship status is null, then give the string not yet shipped. So the hint for this one was to use the timestamp function to determine the difference in days between the order date and the ship date columns. So in our case expression, we have case when, and then we pass in our timestamp diff function. So we have timestamp diff, our unit of time is day, so we don't put any quotation marks around the keyword day, comma, and then we give the 2 dates that we want to get the difference between. So our start date is the order date, then our next argument is going to be the ship date. So all of this function here is going to return an integer, which will be the number of days between the order date and the shipped date. Okay, so when this value is less than or equal to 7, then return the value for those rows, which is shipped within 1 week. Okay, so moving to the next when clause, again we repeat the timestamp diff function, and this time we're going to say when that's greater than 7 days, then it's going to be shipped over a week later. And our last when condition, we have when shipped date is null, then not yet shipped. And you could have put an else keyword in here, but actually we've covered all the scenarios in these 3 when clauses here. So it's not necessary to do, but you could have put it in if you wanted to. Then we have the end keyword, and we're calling this shipping underscore status. So let's click in the query and execute it. Alright, so this gives us the result we wanted. So we can see for order 10248, it was ordered on the 14th of July, and it was shipped 2 days later on the 16th of July. So our shipping status correctly says shipped within 1 week for this particular order. Okay, so another way we could have written this is by using a common table expression. So let's take a look at that. Okay, so I'll just bring this down a bit. Okay, so first of all, we're going to do a common table expression, which I've just called CTE. So to do a common table expression, we have our keyword with. So we have with the common table expression name, so I'm just calling it CTE. Then we have as, and then within a set of parentheses, we have our common table expression, which is like a subquery. So we have select our columns, and then we have the timestamp diff function to get the difference in days between the order date and the ship date. And I'm calling this shipping underscore days. Then we have from OES.orders. We close off the common table expression, and now we can also select from the common table expression. So in the outer query, we have select our columns, and then we have our case statement, but this time we don't need to pass in the timestamp diff into each of the when clauses, because we have just specified it one time in the common table expression, and we've called it shipping days. So now we can reference this shipping days expression in the outer query. So we can have case when shipping days is less than or equal to 7, then shipped within 1 week. When shipping days greater than 7, shipped over a week later. And then our last one is when shipped date, so the actual column, is null, then not yet shipped, and as shipping status. Selecting from our common table expression name, which we specified up here. Okay, so let's click in the query and execute it. And if we bring the query result up a bit, so we get the same result as before, but this time we were using a common table expression to get that result. Okay, let's now move to the fourth challenge. Okay, so for the fourth challenge, you were to get a count of orders by the shipping status as determined by a case expression. So one way of doing this is to do a derived table, which is where we put the subquery and the from clause. So if we look at the subquery first, as that is what gets evaluated first. So we have in the from clause our set of parentheses, we have our subquery, so we have select, case, when, and then we're using our timestamp diff function. So we have our conditions here, and then we have from oes.orders. So in this case, all we need to get is our shipping status expression. Then in the outer query, we have select our new shipping status expression, and then we have the count aggregate function. So we have count within parentheses our asterisk, so count all the rows within each shipping status group. And we're calling this count aggregate function as order count by status, as it is the count of the number of orders within each status. And so we have our select, our from, and then we have group by. So we go group by the shipping status. We always need to alias our derived tables. So in this case, I've aliased the derived table to the letter S. So we have group by s.shippingStatus, and then also in our select statement we have s.shippingStatus. Okay, so let's click in here and execute it. We'll bring this up a bit. Okay, so within the shipped within 1 week shipping status, we have a total number of orders of 473, shipped over a week later, 336, and not yet shipped 21. So we can see that a majority of our orders are shipped within 1 week. Okay, so another way we could have written this query is to use a common table expression. So basically here we're putting what was previously in the derived table into a common table expression, which we're calling in this case just CTE. So we have with our common table expression name as, then within parentheses we have our common table expression, which is as usual our case expression giving us the shipping status. So we're selecting from oes.orders, and then within our outer query we're doing our aggregate function and our group by. So we have select the shipping status, comma, then our aggregate function, which we're calling order count by status, from, selecting from the CTE, and grouping by shipping status. So let's click in here, execute it, and we get the same result as before. Alright, so that's it for the solutions to the case expression challenges. See you next time. Alright, let's now go through date and time functions in MySQL. And for this lecture, we're going to be working through a demo file, so go to the resource link and download the demo file if you want to follow along. Okay, let's now switch to MySQL Workbench. Okay, so we've got Workbench here, and so the next step is to download the date and time function SQL file, which is attached as a resource to this lecture, and then navigate to where you've downloaded it to and open up that file. So I'm just going to click on the Open File button here, and in my case I've got the date and time functions SQL file in my downloads folder. So I'm going to just open that up. First of all, we're going to look at a few different functions that basically return the same thing, which is the current date time. So if I want to know the time right now, I can use select now, and then I have a pair of empty parentheses. And I'm aliasing this function to the name now_value. So let's execute that. Okay, so we can see the query executed on 12/17/44 PM, and that's also what gets returned in the query result here. So we have the date and then the time. So it's the 30th of November 2021. So of course, when you run this, it'll be a different date to this one here. And another way of getting the same thing is to use the sysdate function. So sys is short for system, so it's the system date. So if we execute that, and we get the exact same thing. And a third way to do the same thing is to use the current_timestamp function. And current timestamp is actually a SQL standard function, so in general it should work in other relational databases other than MySQL. And this function does not require any parentheses after it. So we just write current_timestamp and we execute it, and it also returns the current date and time. If we want to include microseconds, then we can do so by passing in 3 as a value into the now function. So if we execute that one, so now we have year, month, day, hour, minute, seconds, and we also have microseconds. Okay, so if we want to return only the current date part and not the time part, then we can use the cast function to cast the result to the date data type. So the syntax for the cast function is we write cast, open parenthesis, we pass in our expression, which is generally a column, and then we do the keyword as, and then we specify the data type that we want to cast the expression to. So in this case we have select cast. Our expression is going to be the value returned by the now function, which will be the current date and time, but we just want to get the date, so we're going to say as date. And then we have a close parenthesis here to close off the cast function. And in this case, I'm just aliasing this whole result to now_date_value. So if we click in here and execute it, so now we just get the date part and we don't have the time component because we cast it to a date data type. Alright, so conversely, if we want only the current time part and not the date, then we can use the cast function to cast the result to the time data type. So this is similar to before, except now we're just casting it to the time data type. So if we execute that, so now we just get the current time, which in my case is 12:22, 17 seconds. Yet another way to extract only the time part is to pass in the now function into another function called time. So we can just write select time, and then we pass in the now function. So we execute that, and we get the current time. Okay, so moving on. Alright, so MySQL also supports UTC date and time functions. And these are functions that return the current date time and universal time coordinated. So here we have some different functions. So we have UTC_timestamp, and this will return a date time value in UTC time. We have UTC date, so this will just return date, and UTC_time will just return the time part, of course in UTC time. Okay, so let's execute all that. And this is the result of those 3 functions here. Okay, so we'll move down a bit. Okay, so let's now go through some examples where we look at some actual date columns. So first of all, we will select some columns from the employees table. Okay, so for each employee, we have their birth date and their hire date. Okay, so let's say we want to just extract out the year part from each date. One way we can do this is to do the following. So we can actually use the extract function to get only the year from the hire date. So the extract function returns an integer representing the specified date part of the specified date column. So we just write extract, and in this case we're going to extract the year from hire date. And we're aliasing this expression to hire year. So if we click in here and then execute it, so now we extract out the year from the hire date column for each employee. Okay, let's now look at some more examples. So we can use extract to extract year, month, and day parts from a date column. So here we have higher year, higher month, higher day, and we just changed the unit for each expression. Okay, so let's click in here and execute it. So now we've extracted out each part of each higher date. Okay, so for the month and the day, let's say we wanted the actual name of the month. So instead of 12, we wanted December. Instead of 11, we wanted November. So instead of 26, what day of the week this was. Was it a Tuesday, a Monday, etc.? So we can get that by using a couple of different functions. So let's have a look at that. Okay, so we can use the function called month name to return the full name of each month, and we can use the function day name to return the full name of each day. So here they are here, and we just pass in our date column, which in this case is higher date, and so let's click on it and have a look at the result. Okay, so this is a bit more readable, so we have the actual month spelled out and also the same for the day. Okay, let's move to the next example. Let's say we wanted to get the count of employees hired in each year. So because we have each year, that means we want to extract out the year from the hire date. And there are a few different ways we can do that. One of them we saw earlier, which was to use the extract function. Another way is to just use the year function. So the year function will just extract the year from a date expression. So we just write year and we pass in our date expression, and it will return an integer value for the year. So in this case, we want to get the count of employees hired in each year, so we need to group by year. So we write group by year, pass in hire date. We also put this expression in our select clause, as that is what we're grouping on, and we're calling this hire underscore year. Then we do our count aggregate function. Okay, so let's click in here and execute it. So in the result, we can see that in 2017, 8 employees were hired, 2006 we had 4 hired, etc. Okay, let's go back to selecting some columns from the table again. Okay, let's now look at a few more functions. So the next function we're going to look at is called date add, and this function can be used to add an interval of time to a date expression. So the syntax for it is date underscore add, and then within parentheses we specify our date expression, comma, then we write the keyword interval, we provide a value, which is an integer value, and then we provide the units that we want to add. So this unit might be day, month, year. So for example, let's say we want to use the date add to add 5 years to the hire date to know when each employee's 5-year anniversary is. So down here we write date underscore add. So we're going to take the hire date column and we want to add 5 years to it. So we write hire date as our first expression, comma, the keyword interval, and we want to add how much? We want to add 5, and then we write the unit, year. And we're naming all of this as 5 underscore years underscore date. So let's click in here and execute it. Alright, so for Jack Bernard, they started in 2017 on the 23rd of January, and Jack's 5-year anniversary at the company will be on the 23rd of January 2022. Okay, moving on. Another function is called dateDiff, and the dateDiff function returns the difference in days between two date values. And the syntax is dateDiff, and we pass in our two dates, and the calculation it does is the first argument's date minus the second argument. So let's use the dateDiff function to calculate how many days each employee has worked at the company as of today. So we're going to have dateDiff, we pass in the current time, which I'm going to do using the current underscore timestamp function. So recall this returned the same thing as the now function, so you could have passed in now in here if you wanted. And then our second date is the hire date. So it's going to go today's date minus hire date. And that will be the number of days that each employee has been employed. Okay, so let's click in here and execute it. So for example, Jack Bernard has been at the company for 1,772 days. Of course, when you run it, you'll get a different number of days to this because you'll be running it at a different time. Okay, let's look at a different way we could have done this, and that is to use another function which is called the timestamp diff function. So this function is used to subtract an interval from a datetime expression, and the syntax is a bit different to dateDiff. So we write timestamp diff, and then our first argument is the unit, which is either day, month or year. Then we have date 1 and date 2. And the calculation is actually in a different order to dateDiff. So in this time, what it's going to do is it's going to do the second date minus the first date. So this is the third argument minus the second argument. So it's in a different order to dateDiff. So if we wanted to do the same as before, which was to get the number of days each employee has worked at the company, we write timestamp diff, then within parentheses, our interval is going to be day, second argument is going to be hire date, third argument is going to be the current time. So it's going to do the current timestamp minus hire date, and then it will return the result in an interval of days. So if we click in here and execute it, and so we get the same result as before when we used the dateDiff. But you can see that timestamp diff is a bit more flexible because we can change the interval. So dateDiff always returns the interval in days, whereas with timestamp diff we could do day, month or year. So for example, let's say we want to get the years employed for each employee. We just need to change the first argument to year. So let's execute that one. So we can see that Jack Bernard has been employed for 4 years, Don Riley 14 years, etc. And if we wanted the months employed for each employee, then we would just change the argument to month. Alright, that's it for the tutorial on date and time functions. See you next time. Okay, welcome to the function challenges. Let's take a look at the first challenge. Concatenate the first name and the last name of each employee. Include a single space between the first and last name. Name this new expression as employee underscore name. Include the employee ID, first name, last name, and your new expression employee underscore name. Coming up are the hints. Query the HCM.employees table. You can use either the double pipe operator or the concat function to concatenate first and last name. Set the session SQL mode to pipes as concat. And to do that, you can use this line of code here, which is set session SQL underscore mode equal to pipes underscore as underscore concat in single quotes. And this line of code here just makes sure that MySQL treats two pipes as a concatenation operator. So this line of code is also necessary for the second challenge. Let's now move to the second challenge. Concatenate the first name, middle name, and last name of each employee. Include a single space between each of the names. Name the new expression employee name. So this time in the select clause, include employee ID, first name, middle name, last name, and your new expression employee name. Coming up are the hints. Be mindful that the middle name column allows nulls. Therefore, you need to use the coalesce function to replace nulls in the middle name column. Concatenate on an additional space to the start of the coalesce function. So recall we used this trick in a previous lecture to only add on an additional space if the middle name actually had a non-null value. Alright, let's now take a look at the third challenge. Extract the genus name from the scientific name as given in the bird.antarctic species table. So the genus name is the first word in the scientific name column. Alright, let's now take a look at the hints. Use the instra function to find the position of the first space. -1 off the result to get the position of the last character for the genus name. Nest this within the left function. So the second argument in the left function will be the result of the instra function, which of course we -1 off. Moving to the next challenge. Extract the species name from the scientific name as given in the bird.antarctic species table. So this time we're extracting the second word, which is the species name, from the scientific name column. Okay, let's take a look at the hints. Use the instra function to find the position of the single space. Add 1 to it to get the position of the first character of the species name. Nest this as the second argument within the substring function. So the second argument of the substring function is where we specify where we want the extraction to start from. And we're determining that by using the instra function and adding 1 to it to get the position of the first character of the second word, which is the species name. Alright, let's now move to the fifth challenge. Return the age in years for all employees. Name this expression as employee age. Include the employee ID, first name, last name, birth date, and your new expression, employee age. Coming up are the hints. Use the timestamp diff function. An employee's age will be the difference between birth date and the current system date time, which you can get by referencing either the now function or the current timestamp function. Recall that the syntax for the timestamp diff function is, first of all, we specify a unit of time, and unit can either be minute, hour, day, week, month, year. In this case, set the unit to year. So we want the age of each employee in years. Then for the second and third arguments, we specify 2 date or date time columns that we want to get the difference in time between. And this returns the third argument, date expression 2, minus the second argument, date expression 1. So recall that later dates are greater dates. So in this case, what we want to do is we want to do the current time minus the birth date. And this will give us the age of each employee. Alright, let's now move to the next challenge. So, assuming an estimated shipping date of 7 days after the order date, add a column expression called estimated shipping date for all unshipped orders, i.e., return only the unshipped orders. Include in your select clause, order ID, order date, and your new expression, estimated shipping date. Coming up are the hints. Query the OES.orders table. Unshipped orders are ones where the shipped date is null. Therefore, use the where clause to keep only orders where the shipped date is null. Use the date add function to add 7 days to the order date. And the syntax for the date add function is date underscore add. Then we first of all pass in our date or date time column, comma, and then we have the keyword interval. Then after the interval keyword, we specify an integer value for the amount of time that we want to add on. So in this case, it's going to be 7. And then unit is the unit of time. And in this case, our unit will be day. Alright, let's now move to the next challenge. Calculate the average number of days it takes each shipping company to ship an order. Call this expression average shipping days. So include the company name and your new expression, average shipping days. Coming up are the hints. Join the OES.orders table to the OES.shippers table in order to get the company name. Group by company name. In the select clause, use the timestamp diff function to calculate the difference in days between order date and shipped date. Nest this result within the average aggregate function to get the average for each shipping company. Alright, so give those 7 challenges a go, and coming up next, we will go through the solutions. Okay, let's now go through the solutions to the function challenges. So, before the first challenge, we were to set the SQL mode to pipes as concat. So let's just click in here and execute that line. Okay, so now MySQL will recognize double pipe as being a concatenation operator. So for the first challenge, you were to concatenate the employee first name and last names together. So we have first name, double pipe, then we concatenate on a single space, concatenate on the last name, and we're calling all of this expression employee underscore name. And of course we're selecting from the hcm.employees table. Okay, so I'll click in there and execute that. So there we have it, we have each employee's full name. Okay, so another way we could have done this is that we could have done the concat function. So with the concat function, we just list all the expressions in a comma delimited list that we want to concatenate together. So we have concat first name, comma, a single space, comma, last name. And again, I'm calling this employee name. So if we click in here, execute it, and we get the same result as before. Okay, so moving to the second challenge. So the second challenge, we're also doing employee name, but we're adding in the middle name in the middle here. Okay, so to do this, we do first name, concat on middle name, but recall that middle name does allow nulls. And therefore, what we need to do is we need to put it in the coalesce function to replace nulls with a blank, which is just an empty string. So if middle name is null, we're going to replace it with an empty string, and we're just going to get first name concatenated on with a space here and then last name. Now if middle name does have a value, then what we want to do is we want to concatenate on a single space before middle name. So if middle name has an actual value, then we get first name concatenate on single space middle name, concatenate on single space last name. So that's the trick we use by putting this single space on at the beginning here of the middle name to only add a space if middle name has a non-null value. Okay, so let's click in here, execute it, and there we have it. So we have Jack, John, Bernard, etc. And if we scroll down a bit here, we can see that for people who don't have a middle name, for example for John, Jen, we only get a single space between them. And this is what we wanted. And we could have also written this one using the concat function, and to do that, we would have written it like this. So again, we're using that same trick here for the second argument for the middle name. So let's click in here, execute it, and that gives us the same result. Okay, let's now move to the next challenge. Okay, so for the third challenge, you were to extract the genus name from the species scientific name as given in the bird.antarctic species table. Use the instra function nested in the left function. Okay, so in our query here, if we look at the expression that we've added on, first of all, we'll take a look at the innermost function, which is the instra function here, as this is what gets evaluated first. And the instra function is used to find the position of some character within an expression. So our expression here that we're searching is the scientific name column, and we're finding for each row the occurrence of a single space character. So we're going to find the location of the first single space within the scientific name column on each row. So this returns the number, and then we minus 1 off it to get the position of the last character of the first word in the scientific name column. So once we have that position, we can then nest it within the left function. So the left function returns the leftmost characters, so starting from the left hand side, up to some location that we specify in the second argument. So we're going to return the leftmost characters from scientific name up to the last character of that first word. And this is the genus name. So we alias this whole thing as genus name. Okay, so if we click in here and execute it, so there you have it. So we get the genus name, which is the first word for each species. Okay, let's now move to the fourth challenge. So for the fourth challenge, you were to extract the species name from the scientific name. So this time we want to get the second word from the scientific name. So you were to use the instra function nested in the substring function. So the substring function extracts out some substring from a string. So the string we're going to pass in is the scientific name column. The second argument is our start position. The third argument is where we want to extract to, and in this case we can leave it out because we want just everything past the start position. Okay, so in the second argument we have the instra function, we pass in the scientific name again, and we're searching for the location of that single space, which is the single space between the two words. But this time we're going to add one to it, and that's to get the position of the first character in the second word for each row. and we're going to alias this whole thing as species name. So I'll just click in here and execute it. So now we get the second word returned, which is the species name. Okay, moving to the next challenge. So for this challenge, you were to return the age in years for all employees. So one way of doing this is to use the timestamp diff function. So we have timestamp diff. The first argument is our interval of time. So in this case, it's going to be year, comma. Then we specify the two dates that we want to get the difference between. And the first date is our starting date. And so that's going to be our birth date. And then our third argument is going to be the current time. And we can get the current date time by using the current underscore timestamp function. An alternative you could have used would be to use the now function. So you could have written now with a pair of parentheses after it. The current underscore timestamp function doesn't require a set of empty parentheses after it like the now function does. Okay, so we alias this whole thing as employee age. And we're selecting from the hcm.employees table. Okay, so I'll just click in here, execute it. So now we have the age of each employee. So Jack Bernard is 27 years old, Don Riley 54, etc. And note that depending on when you watch this video, you may get different ages as it's further on in time. Okay, so let's now move to the next challenge. So for this one, we were assuming an estimated shipping date of 7 days after the order date. Add a column expression called estimated shipping date for all unshipped orders. So in this one, we were to use the date add function to add 7 days to the order date. So the syntax is just date add. First argument is our expression order date. Then we do comma, and then we write the keyword interval. We specify our interval of time that we want to add to the order date column, which is going to be 7, and then we write our unit of time, in this case, day. And we're going to name all this estimated shipping date. And also we're only interested in the unshipped orders. So these were ones where shipped date is null. So click in here, execute it, and now we get the estimated shipping date for each order. Okay, so let's look at the next challenge. So this challenge was a bit more complicated, and it was to calculate the average number of days it takes each shipping company to ship an order, and we were to call this expression average shipping days. So first of all, we have each shipping company. So we want to group by each company as given by the company name column. And we get the company name column from the shippers table, which I've aliased to S in this case. So we have orders O joined to shippers S, joining on the shipper ID, and then we can get the company name. So we can then group by shippers.company name. And so we also put shippers.company name in the select clause. Then we use the average aggregate function, and within the average aggregate function, we're going to place our timestamp diff calculation to calculate the difference in days between the order date and the shipped date. So in other words, for each order, we're calculating the difference in days between the order date and the ship date. We are then grouping this by company name. Then we're calculating the average number of days it takes in order to ship for each company. Okay, so let's click in here and execute the query. So if we look at the result here, we can see that Fast Freight Company, they can ship in an average of 8.59 days. Smart Shipping, 9.2 days. And Pack and Ship are the fastest at an average of 7.44 days to ship orders. And another way we could have done this is to use the date diff function rather than the timestamp diff function. So if we have a look at this one, we could have done date diff, and just note with date diff that we specify the dates in a different order. So we do the ship date first, then the order date. And also note that date diff is a bit more limited than the timestamp diff function in that it only returns the result in days. Whereas with the timestamp diff function, we have that flexibility to specify different units of time, for example, month, year, week, etc. Alright, so that's it for this lecture. See you next time. Hello everyone, and welcome to the Views lecture. Let's get straight into it. So a view is a virtual table whose data is defined by a query. So essentially, you can think of a view as being like a saved query. And the basic syntax for a view looks like the following. So we have the keywords create view, then we give the schema name dot view name, so the name that we want to name the view. Then we have the keyword as, and then after that we have the select statement which defines the view. So anytime anyone queries the view, the select statement in the view will be executed against the database. Okay, let's go for an example. So here we are selecting all the columns from a table of employees. But let's say we wanted some people to only be able to query data from this table, but we don't want people to see the salary column. So one way we can do this is to create a view which includes all the columns that we want to be visible, but we could exclude the salary column from the view. So let's select all the columns except for the salary column. Okay, so here's our query here, and all we need to do to turn this into a view is we just add the following line before the select statement. So now we are creating a view. So we have create view, we give the schema where we want to store the view, and then we give the view name. So in this case, we're just calling it employee_info. We have the as keyword, and we have our select statement. So once we've created this view, then we can query it just like we can query a table. For example, if we write the following query, select all the columns from the newly created view, then we'd get the following result. So now we can give people in the organization access to the view rather than the base table in order to restrict the information that they can see. To summarize, like a table, a view consists of named columns and rows of data. Unlike a table, a view has no physical representation. What I mean by this is that the data in a view is not stored on disk. Instead, a view typically queries base tables. So in other words, a view fetches data from underlying tables when we query the view. So a view is always up to date. So when we query the view, it's going to go and fetch the data from the underlying tables based on the select statement query in the view. Let's now take a look at some more characteristics of views. Every column in a view must have a name, and that name must meet the same naming requirements as a base table. For example, a column name cannot start with a number, etc. Some views are updatable. That is, you can use them in statements such as update, delete, or insert statements to modify the data in the underlying table. For a view to be updatable, there must be a one-to-one relationship between the rows in the view and the rows in the underlying table. So if we had a view that used a group by clause to group the rows, then this would be an example of a view that was not able to be updated because each group would be one row, and that would of course map to multiple rows in the base table. Okay, let's now cover some situations where it would be useful to have a view. So firstly, as we've covered, a view can be used to provide security in terms of limited access. Users can have access to views that select only a subset of columns from a table. So we've already seen an example of how this can be used. Another good reason for creating a view is that views can be used to simplify a data model. For example, you could have a view which has a complex select statement which joins multiple tables and or aggregates data. Users can then query the custom-made view to simplify reporting queries. Alright, let's now go for a quick challenge. For this challenge, try creating a view from one of the queries you have previously written, then query the view. And just one note, and that is to make sure to include the schema name for the schema where you want to save the view. For example, here is the first line of a view where we are creating a view called employee details in the HCM schema. So we just have the schema name dot view name. Okay, so pause the video and give that a go. Alright, so now I'm going to switch to MySQL Workbench and go through views in a bit more detail. Okay, so I've got the views demo SQL file open, and if you want to follow along, the SQL file will be attached as a resource link to this lecture. Okay, so here I've got a query that gives the average salary in each department ordered from highest to lowest. So all we're doing is we're joining the employees table to the departments table, and we're using an inner join, so we're only going to return employees who actually do belong to a department. And then we're grouping by both the department ID and department name. So we want both these columns in our select clause. And then we're calculating the average salary in each department. And finally, we are ordering by our new average salary expression, and we're ordering in descending order. Okay, so if we highlight all that, click on the execute selected portion button. Okay, so we get our query result here. And let's say we want to save this query in a view. All we need to do is take the query, and then we just put one line at the top here. So we have create view, the schema name, and then the view name. So I'm calling it department underscore avg underscore salaries. We have the keyword as, and then we just put in our select statement. Okay, so I'm going to highlight that and execute it. Alright, so that has created the view. So now we can select from the view. So let's highlight that, execute that. Okay, so we're getting an error here, and actually I forgot to include the schema name. And at the moment you can see that the default schema is Sakilla. We can always change that using a use statement, but generally it's best to actually write the schema name when we reference objects. So I'm just going to type it in now, hcm.department_average_salaries, select it, execute it. Okay, so there we have it. So we don't have to write that query each time. We can save the query as a view, and then we can select from that view. So even if we close down MySQL Workbench, open it up again, this view will still be here. And one other thing I want to show you is that if we need to make some modifications to an existing view, we can do so by using a create or replace view option. Basically, it's very similar to before, it's just that we've added in these keywords here, or replace. So this will create a view if one doesn't exist, or if a view does exist with that name, then it will replace it with the new select statement. So in this case, we're just making one small change, and that's to round the average salary. And we're rounding the average salary to 1 decimal place in this case. Okay, so if we select that one and execute it, so that has recreated the view. And if we select from it again, and now we can see we get a nicer result with these average salaries rounded to 1 decimal place. Alright, that's it for now. See you next time. Hello and welcome to this lecture on the create table statement. Let's get started. To create a table in MySQL, we can use the create table statement. So shown here is the basic syntax for how to create a table. So we have the keywords create table, and then we give the table a name, and then within parentheses we specify the column definitions as well as any constraints we want on those columns. So we name the first column, and then we have a space, then we give the data type for that column, and then we have the option of specifying a not null constraint. So if we specify a not null constraint, then we will not be allowed to insert nulls into that particular column. Okay, so after each column definition we have a comma, then we move on to the next column, so we specify the next column name, data type, and so on. And then after the last column definition, we specify any constraints that we want applied to any of these columns. To show this, let's now look at an actual create table statement. So here we are defining a table called departments, and we have 2 columns in this table, which are department ID and department name. So we are giving the department ID a data type of int for integer, comma, then we go to department name, we're giving this one a data type of varchar 50, so variable character all the way up to 50 characters maximum. And we are also putting a not null constraint on the department ID column. So department ID will always need to have some non-null value in it. The same is true actually for department ID. However, we didn't need to specify not null here because that will automatically get added on when we add on a primary key constraint to the department ID column. So after the last column, we have a comma, and here is where we specify our constraint or constraints. So we have the keyword constraint. We give the constraint a name. So in this case, I've named it PK department ID. And then we give the type of constraint. So this constraint is a primary key constraint. And then within parentheses, we specify the column or columns that we want to apply the constraint to. So we are giving the department ID a primary key constraint. And that will mean that department ID must have unique non-null values. Therefore, we will not get any duplicate values for department ID. Okay, so on the last line here, we have a parentheses to close off the create table statement. And as usual, we have a semicolon to finish our SQL statement. A common thing to add to an integer primary key column is the auto increment property. This has the effect of auto incrementing values when we insert rows to the table. Okay, so let's add that on. So now we have given the auto increment property to the department ID column. So we have department ID, the data type, and then we've written auto underscore increment. So what this is going to do is it's going to start from a value of 1 for the first row inserted into the table, and then it will increment by 1 for each row we insert into the table. So the second row will get a value of 2 for department ID, third row value of 3, etc. Okay, let's now create another table, and we'll also look at how we can define a foreign key constraint. So here we are creating a table called employees. So again, we just do create table, give our table name, and then within a set of parentheses, we have the table definition. So first of all, we define some columns with their data type, and then we have the constraints. So after the last column definition, we have comma, and the first constraint is a primary key constraint on the empid column. And empid is an integer column with the auto increment property on it. Okay, so then if we look here, we have a comma, and then we can define our next constraint. And this constraint here is a foreign key constraint on the department ID column in this table. And this foreign key references back to the department ID column in the departments table. So the departments table is our parent table. So recall that typically a foreign key references back to the primary key of the parent table, and that's exactly what we've specified here. So because we're placing a foreign key on this department ID column, this means that we can only enter department ID values into the employees table if they exist in the department ID of the departments table, which is our parent table. So the syntax for defining a foreign key constraint is, again, we have the keyword constraint, we give the constraint a name, and how I like to name my constraints is I'll have the constraint type abbreviation, so FK for foreign key, then I'll have the table name, and then the column name. In this case, I've abbreviated the column name as well, just so I can fit it onto the screen here. Okay, so after we've named the constraint, we give the constraint type. In this case, it's a foreign key. Then we define the column or columns, which are to have the foreign key applied to it. So just like the primary key, we put this in parentheses. But with a foreign key, we need a bit more information, and that is to specify what it's referencing. So to do that, we write the keyword references. Then we give the parent table name, and more specifically, we give the column in the parent table, which the foreign key is to reference. So we put this in parentheses as well. Okay, let's now open up MySQL Workbench and go through a demo where we will create a couple of tables and populate them with data. Okay, so I've got MySQL Workbench open, and if you want to follow along with this demo, then just open up the create table demo file, which is attached as a resource to this lecture. Okay, so the first thing we're going to do is we're going to create a new schema called DBO. Okay, so I'm going to click in the statement and click on the execute I button. Make sure you don't click on this button as it will just run the whole script. Okay, so I'll click on that one. and we can see here we've got create schema DBO. So that has created a new schema, and if we click on the refresh button here, so now we can see our new schema DBO. So now we can create some new tables in this schema. Okay, so the first table we are going to create is called parks1. So we have create table, then we have the schema name dot table name. So we have dbo.parks1, then within parentheses we specify our columns and data types. So the first column is called park ID and it's of data type int, so integer. We do a comma, move to the next column which is park name. This is variable character, varchar, up to 50 characters long, comma, and then we have the entry fee. So the entry fee is going to be the amount of money that people have to pay to access the park. So entry fee is going to be decimal, and we have 6,2. So 2 of the 6 digits are reserved for decimal places. So the largest number we can have with 6,2 will be 9,999.99. So 6 digits in total, 2 digits reserved for decimal places. And that number should be more than enough to enter a park. Okay, so let's click in here, click on the execute I button, and that has created a table called dbo.parks1. Okay, let's now select from this table. So as you can see, we currently have an empty table. So all we have is the column headers. Let's now insert some data into this table. Okay, so to insert rows, we can use the insert statement. And we will be covering the insert statement in greater detail in a later lecture. But for now, to write an insert statement, all we do is we write insert into, we give the table name, we specify the columns, and then we have the keyword values, and we specify the value for each column. So park ID is our first column specified. We're going to insert a value of 1. Park name will be Belmont Park, and entry fee will be 5 for this particular row. And there is a different way to write this, but for now we're just doing a separate insert statement for each row. Okay, so let's highlight all of that and click on the execute the selected portion button. Okay, so we have 1 row, 1 row, 1 row, so we have 3 rows inserted. So let's now look at the table again, and we can see our few rows of data here. Okay, so let's now create another table called parks2. So this table will have the same columns as parks1, but we're going to make a couple of improvements. So first of all, we're going to make park ID an auto-incrementing column. So we're going to write park ID int auto_increment. And as mentioned earlier, this means that each time we insert a row into a table, it's going to automatically generate a value for the park ID. And this means that we don't need to specify static values in the insert statements. Okay, so we have park name, entry fee, and then we're also going to add on a constraint. So this time we're going to have a comma after the last column, and then we define our constraint. So we're going to put a primary key constraint on the park ID column in this table. So we have constraint, the constraint name, constraint type, and the column on which the constraint is to be applied. So this primary key constraint will ensure that park ID will always be unique and not null. Okay, so click in here and click on the execute I button. So that's created the table, and let's now insert some data into that table. So now notice with our insert statement that we haven't specified park ID as a column name here. So we just have park name and entry fee. So for the values for this one, we've got Belmont Park, entry fee $5. So we don't need to specify park ID because it's automatically going to get generated as it has the auto increment property on it. So let's just highlight these few insert statements and click on the execute selected portion button. Okay, so let's now select from that table. As you can see, park ID has been automatically generated in a sequential order. Okay, let's now create a child table to the parks2 table. So here we are creating a child table called park visits. So we can have one or more visits to each park. And park visits is going to record all the people who visit a particular park and at what time they visited the park. So we have create table dbo.parkvisits. Within parentheses, we specify our columns. So we have visit ID. This is going to be our primary key, and it's integer, has the auto increment property. And then we have park ID, which is going to be the ID of the park they visit, the visit date, and their first name, last name. So our first constraint is going to be a primary key constraint on the visit ID column. We have comma, and then we specify our second constraint, which is a foreign key constraint on the park ID column. So it's placed on the park ID of this table, and it references back to the park ID column of the parks2 table. So we write references, the parent table name, and then within parentheses, the primary key of the parent table. So this will ensure that we can only insert park ID values into the park visits table that first exist in the park ID column of the parks2 parent table. So this gives us our referential data integrity. Okay, so I'm going to click in the statement, click on the execute I button to create this table. Okay, so that has created the table. Now we're going to insert some values into the table. And when inserting rows, we don't need to specify the auto increment column. So in this case, visit ID is the auto increment column. So we don't need to specify it in our insert statement as it gets automatically generated. So we just need to give the park ID, the visit date, first name, last name. So let's highlight these rows and click on execute selected portion button. Alright, so those rows have been inserted, and let's now just select the data from the table. So we have 4 visitors to the various parks. And just for demonstration, let's now try to insert this new row here and see what happens. So we'll highlight this and execute it. Okay, so here we get an error message, which is cannot add or update a child row, a foreign key constraint fails. So what happened here is that this row cannot be inserted because the park ID value of 99 does not exist in the parks2 parent table. The foreign key ensures that values inserted into the park ID of the park visits table must match an existing value in park ID of the parks2 table. At the moment, we don't have any park ID 99 in the parks2 table. So we would first need to add this park with a park ID of 99 to the parks2 parent table before we could insert a visit to this park. So this foreign key helps to make sure that our data is consistent across tables. So if you made some mistake during the demo, say for example you accidentally ran the whole script at once, what you can do is you can drop the tables and start again. So to drop a table, which means to permanently delete the table, you can write drop table and then give the table name. So first you need to delete the child table and then you can delete the parent table. So if I wanted to permanently delete the park visits table, I'd write drop table dbo.parkvisits, end it with a semicolon, and then you can drop the parks2 table and the parks1 table. So you can write drop table dbo.parks1, and I'll just copy that and drop table dbo.parks2. So if you run those 3, it will permanently delete them. I won't do that for now, but that's how you can do it. And we'll be covering the drop table statement in a later lecture. Alright, that's it for now. See you next time. Hello and welcome to this lecture on the insert statement. We have already seen some insert statements in the previous lecture, but this time we're going to cover the statement in greater detail. We will also look at how we can insert the output of a select statement into a table. Alright, let's get straight into it. The insert statement is used to insert rows into a table. Shown here is the basic syntax for an insert statement. So first we have the keywords insert into. Then we give the name of the table we are inserting the row into. Then, in parentheses, we specify the column names in a comma-separated list. After that, we have the values keyword, and then after the values keyword, we have another set of parentheses, and this is where we specify the actual values to be inserted, and these are also in a comma-separated list. The values to be inserted need to be in the same order as the corresponding column names specified in the first set of parentheses. Let's now take a look at an example. So here we are inserting one row into a table called products, and we are inserting the values into the prod name, unit price, and last updated columns. Then we have the values keyword, and after the values keyword we have our next set of parentheses where we actually specify the values to insert. So in this case, we are inserting a value of A2 milk for the prod name column, a value of 4.9 for the unit price. And note that 4.9 did not need any quotes around it because unit price is a numeric data type column. Then we have a date value of 2020, November the 27th, which will go into the last updated column. The last updated column is a date data type column, and so we are using the format year, month, day, and digits, and we put this in single quotes. In this example, I have put the values clause on a new line. However, we could have put this whole statement on one line if we wanted to. Remember that SQL doesn't care about line breaks. Now, if we wanted to insert multiple rows, then one way of doing this is to simply have multiple insert statements like the one we have here. Another way we can insert multiple rows is by doing the following. So now in this insert statement, we are inserting 4 rows into the products table. So after the values keyword, we have a set of parentheses for the column values in a comma separated list for the first row to be inserted. Then we have a comma, and then we have the values for the next row in a set of parentheses, comma, then the next row, and so on. Okay, let's now look at how we can insert data which comes from another table or tables. We can use the insert into select statement to insert data that comes from another table. And the syntax for it looks like this. So we have insert into our table, then we specify the columns in a comma separated list, which is all enclosed in parentheses. Then we have our select statement. So essentially what is happening is that the output of the select statement will get inserted into the table. Let's look at an example. So in this example, we are inserting into a table called DBO dept, and more specifically the dept name and lock ID columns. Then on the second line we have our select statement, which is select department name, location ID from departments table, where department name equals IT. So the output of the select statement will get inserted into the DBO dept table. In the next challenge, you'll be creating this table and inserting some data into it. Sometimes you will see an insert statement which does not specify the column names of the table, that is to have rows inserted into it. However, it is best practice to specify the column names, just in case in the future there might be some schema changes made to the target table. For example, maybe a column is removed and this changes the column order, and therefore you might inadvertently end up inserting data into the wrong column if you have not specified the column names in the insert statement. Okay, thanks everyone, that's it for this lecture, and I'll see you in the next one. Hello and welcome to the Create Table Challenges. In this set of challenges, you'll be creating a couple of tables and also populating them with data. Let's get started. So for the first challenge, you are to create a table called dept in the DBO schema and specify the following columns: dept ID of data type int and dept name of data type varchar50. Give the auto increment property to the dept ID column. Also, put a primary key constraint on the dept ID column. Put a not null constraint on the dept name column. So dept ID will also have a not null constraint, but you don't need to specify that because it automatically gets added on when you add on the primary key constraint. Note, if you have not already created a schema called DBO, then you can do so with the following statement: create schema DBO. So if you're following along with the previous demo, you may have already created the DBO schema. But if you haven't, then you can run this line of code before you create the table. Okay, let's have a look at the hints. A not null constraint is defined in line after the data type, whereas typically a primary key constraint is defined after the last column's data type. Okay, let's now move to the second challenge. So for this challenge, you are to write an insert statement to insert the following row into the dbo.dept table. So we want a value of 1 for the dept ID and a value of business intelligence for the dept name. Okay, so coming up are the hints. You do not need to specify the dept ID column in the insert statement because it is automatically populated due to the auto increment property on that dept ID column. And recall that the insert statement syntax is just the keywords insert into. We specify the columns. So in this case, we're just going to be specifying one column. And then we have the keyword values, and we specify the corresponding values for each column. So in this case, we're just going to have one value, which is going to be business intelligence. Alright, so let's now move to the next challenge. So in this one, you are to populate the dbo.dept table with more rows. So insert all the department names from the hcm.departments table. Coming up are the hints. Use a select insert into statement to select department names from the hcm.departments table and insert them into the dbo.dept table. Note that you only need to include the department name column in the select statement. And again, that's because the dept ID is automatically generated due to that auto increment property. Alright, let's now move to the next challenge. So for this challenge, you are to create a table called emp in the DBO schema, and then you are to specify the following columns. So specify all these columns here. Give the auto increment property to the emp ID column. Also, put a primary key constraint on the emp ID column. Put not null constraints on any columns you think might need them. Put a foreign key constraint on the dept ID column, which references back to the dept ID column from the dbo.dept table. Okay, let's now take a look at the hints. As a reminder, the syntax for a foreign key is constraint, the constraint name, constraint type, foreign key. Then we specify the child column. So in this case, it's going to be dept ID. And then we have the keyword references. We give the parent table name, which is going to be dbo.dept, and then the parent column, which is the primary key that the foreign key is referencing. Alright, let's now move to the next challenge. So for this one, you're to populate the dbo.emp table with the following two employees. So we have Scott and Miriam. Let's now look at the hints for this one. You do not need to specify emp ID in the insert statement as it has that auto increment property, and for the hire date column, use the standard format of year, month, day, and digits. And we also put these in single quotation marks. Okay, so have a go at doing those 5 challenges, and next up we will go through the solutions. Hello and welcome to the update statement lecture. Let's get started. The update statement is used to update existing data in a table. So with the update statement, we are modifying existing rows. Okay, let's have a look at the basic syntax for an update statement. So we have the keyword update, then we give the table name, and then we have the keyword set, and we set a column equal to a value. And we also have an option of setting multiple columns if we want to, and we can do this by just doing a comma and then specifying the next column and then the value that we want to set it equal to. Then last of all, we have the option of specifying some where conditions. So the where clause is optional. However, most updates will have a where clause because generally we only want to update a subset of values in a column and not all the values in a column. An example of a typical update statement is the following. So in this example, we are updating a table called products and we are setting a column called price equal to 5.5, but only where the product name equals sports hat. So after we execute this update statement, all the rows in the table which have a product name equal to sports hat will get a new price of 5.5. Another way we can do an update statement is that we can actually update a column to some expression. So for example, we could have something like the following. Now in this example, we are setting the price equal to itself, so price multiplied by 1.1 for all products with the product name sports hat. So this has the effect of increasing the price by 10% for any products named sports hat. We can also update the values in multiple columns or within the same update statement. So let's have a look at that. So now we are updating both the price column and the category name column. So we just have a comma at the end of setting the value for the price column, and then we're setting the value of the category name column. So we're setting category name equal to clothing, where product name equals sports hat. Okay, let's now go for a quick challenge for you. In this challenge, you are to use an update statement to change Miriam's last name from Yardley to Greenbank in the dbo.m table. Identify Miriam by her EMP-ID number in the where clause of the update statement. Note that the dbo.m table is created and populated with rows in a previous challenge. If you have not done that challenge, then you can execute the SQL file attached to this lecture called Create and Populate Tables Dept and EMP. So note that you'll need to create both the Dept and EMP table because Dept is a parent table to the EMP table. Okay, so you might want to pause the video and give that a go. Now let's switch to MySQL Workbench and go through the solution. Okay, so first of all, I'm just going to select from the dbo.emp table to have a look at the data in the table. Okay, so we have two employees, Scott and Miriam, and our task was to change Miriam's last name from Yardley to Greenbank. So we just have update the table name, dbo.emp, then set last name equal to Greenbank and single quotation marks, and then we have our where clause where EMP-ID equals 2. So we can see from here that Miriam is EMP-ID 2, and it's always best to identify employees by their EMP-ID, and this is because we may have two employees who happen to have the same name, but we can rely upon the EMP-ID to give us our unique value for each employee. Okay, so I'm going to highlight this query and click on the Execute Selected Portion button, and we get our message down here that the update statement has run successfully and one row has been updated. So let's now select from the table again, and there you have it. Now we have Miriam Greenbank. Okay, that's it for the lecture. See you next time. Hello and welcome to the delete statement lecture. Let's get started. The delete statement is used to delete rows from a table. Let's look at the basic syntax for a delete statement. So we have the keywords delete from, then we give the table name that we want to delete rows from, then we have the option of specifying some conditions in a where clause. If we did not include a where clause, then we would end up deleting all the rows in a table. Most of the time, you'll only want to delete some specific rows from a table, and therefore most delete statements will include a where clause. Let's take a look at an example. In this example, we have delete from dbo.products, where product name equals sports hat. So this statement will delete rows from the products table which have a product name of sports hat. Let's now take a look at another example. So now we just have delete from dbo.products, and this statement will delete all rows from the products table. And note that another way to delete all the rows in a table is to use a truncate table statement. We will be covering the truncate table statement and how it is different from a delete statement in an upcoming lecture. Okay, let's now go through a quick challenge. Use the delete statement to delete employee Scott Davis from the dbo.emp table. Identify Scott by his emp ID number in the where clause of the delete statement. And note that the dbo.emp table is created and populated with rows in a previous challenge. If you have not done that challenge, then you can execute the SQL file attached to this lecture called create and populate tables dept in emp. Okay, so pause the video and give that a go. Alright, let's now switch to MySQL Workbench and go through the solution. Okay, so first of all, we're going to select from the dbo.emp table. And so we have our two employees, Scott and Miriam, and notice that Scott has an emp ID of 1. So for our delete statement, we're going to go delete from dbo.emp, where emp ID equals 1. So this will delete this whole row here for Scott. So let's say Scott is no longer an employee and we want to delete his row. This is how we go about doing it. Okay, so I'll highlight the delete statement and click on the execute the selected portion button. Okay, so we've got one row affected, and let's now select from the table again. And now we just have Miriam as the only employee, and we have deleted Scott. Alright, so that's it for the lecture. See you next time. Hello and welcome to the truncate table statement lecture. Let's get started. The truncate table statement can be used to delete all the rows in a table. Let's have a look at the syntax for it. So the syntax is very simple. We just have the keywords truncate table, and then we give the table name for the table that we want to truncate, i.e. delete all the rows from. For example, so here we are truncating a table called dbo.products. Previously, we saw how we could do the same thing using a delete statement. However, there are some important differences between delete and truncate table. Let's go through these differences. Okay, so first of all, the delete statement is used to delete specified rows, and we can delete either one or more rows. Whereas the truncate table statement is used to delete all the rows from a table. And following on from this, most delete statements have a where clause. If a delete statement does not have a where clause, then all the rows are deleted. On the other hand, a truncate statement does not allow a where clause. In other words, truncate table will always delete all the rows in the specified table. Delete is what's known as a data manipulation language statement. So delete, update, insert, these are all DML statements. Whereas truncate table is what's known as a data definition language or DDL statement. DDL statements also include things like create table and alter table. The delete statement is executed using a row lock, i.e. each row in the table is locked for deletion, whereas truncate table is executed by locking the whole table. Delete logs each row that is deleted in a transaction log, whereas truncate table does not log individual row deletions. And for this reason, truncate table is faster than delete. However, in MySQL, truncate table cannot be rolled back even if it is within an explicit transaction. So basically we have to be a bit more careful with truncate table because we can't roll it back. One interesting thing is that in SQL Server database, you can actually roll back a truncate table if it is within a transaction. But within MySQL, you cannot do this. So in MySQL, it's more final. If you do a truncate table, you can't roll it back, even if it's within a transaction. Okay, so moving on. Delete does not reset a column which has the auto increment property. Now this is true for MySQL's default storage engine, which is called NODB. But there are some exceptions to this behavior. And if you want to learn more about this, then check out the links to the MySQL documentation in the file attached to this lecture. But generally it's true that if you do a delete statement, it's not going to reset the auto increment property. So let's say you have a primary key auto increment column called ID and it's up to number 4, and you delete all the rows in the table, then you insert a new row. Well, that new row is going to get a value of 5. It's not going to reset the auto increment. On the other hand, a truncate table will reset a column which has the auto increment property back to the seed value of 1. So again, if you have 4 rows in a table and you're up to value 5 for the next auto increment, if you truncate that table, then the next row you insert is going to have the value of 1 for the auto increment column. Okay, and last of all, the delete statement can be used on a table that is referenced by a foreign key, provided that there are no related rows in the child table, whereas truncate table cannot be used on a table that is referenced by a foreign key in another table. So if you wanted to use truncate table, you'd have to first remove the foreign key referencing that table, and then you could do the truncate table. Alright, that's it for now. See you next time. Hello everyone, and welcome to this lecture on the alter table statement. So we can use an alter table statement to change the structure of a table. Okay, let's get started. The alter table statement can be used to add, modify, rename, or drop columns in an existing table. Note that in SQL we use the term drop when we delete an object such as a table, column, etc., whereas we use the word delete when deleting a row. We will cover more on the drop table statement in a future lecture. Okay, with that aside, let's look at some alter table statements. Given here is the basic syntax for how we can use the alter table statement to add a column to a table. So first of all, we have the keywords alter table, and then we give the table name of the table that we want to alter. And if we want to add a column, we have the keyword add, and then we give the new column name, followed by the column's data type. Then if we want to, we can specify where in the table we want to create the column by using either the first or after keywords. And if we're doing the after keyword, we specify the column that we want to add the new column after. We'll take a look at that in just a moment, but first let's look at a simple example. Okay, so in this example we are adding a new column called product code of type int to a table called dbo.products. So we just have alter table, the table name, dbo.products, the keyword add, then the column name and its data type. And the default is that the column will get added to the end of the table. Now let's say we instead wanted to add the product code column after another column called product name. To do that, we can use the following syntax. So now we just write the keyword after, and then we have product name. So now the product code column will be added as the next column after the product name column. Okay, let's now look at how we can add multiple columns to a table, all in one statement. So the syntax is very similar to before, but this time all we need to do is use a comma to separate each column definition. So we have add our first column, and then we give the column definition, then we have a comma, and then we have add the second column, and then second column's definition, etc. Alright, let's have a look at an example. So here we're adding 2 columns to a table called dbo.products. So first of all, we're adding a column called product code. We give it data type, we have a comma, then we repeat the add keyword, and then we specify the next column and its data type. So the next column here is called date added, and it's of data type date time. Okay, let's now look at how we can modify the column definition for an existing column. So we can modify an existing column by using an alter table modify statement. And we use the modify keyword when we want to change the data type of a column. So the syntax is just alter table, we give the table name, then we have the keyword modify, followed by the column name that we want to modify, and then we add the new data type that we want to change the column to. Okay, let's look at an example. So in this example, we are modifying the product name column in the dbo.products table, and we're changing the data type to varchar 50. So imagine if previously this column had a data type of varchar 20, but now we had some new products with some very long product names, and therefore we want to lengthen the column. In this situation, we can use this statement to do just that. So we lengthen the product column name so that it can store strings up to 50 characters. We can also use this statement to add on a not null constraint. For example, okay, so now after the data type, we just add on not null. So now we have added on a not null constraint to the product name column. But note that if the table already has some nulls in the product name column, then this statement would not work. We would first need to remove the nulls from the column before we could add on a not null constraint. Okay, let's now look at how we can use an alter table statement to drop a column from a table. So to drop a column from a table, which is to permanently delete that column from the table, we have the syntax alter table, we give the table name, and then we have the keywords drop column, and then we give the column that we want to remove. For example, so in this example, the column called color, as well as all the data in this column, is permanently removed from the database table. Alright, let's take a look at how we can rename a column in a table. To rename a column in a MySQL table, we can use an alter table change column statement. So we have alter table, our table name, then we have the keywords change column, then we give the old column name, followed by the new name that we want to name the column. Then we specify the column data type. And again, we have this usual option to specify where we want the column in the table. And just note that we must specify the column data type when renaming a column, even if we do not change the data type. Okay, let's take a look at an example. So in this example, we are renaming a column called CNAME to contact name in a table called contacts, and we specify the data type as varchar 20, and this also has a not null constraint on it. So just be aware that changing a column name can break scripts, store procedures, and views that are referencing the old column name. So it's important to check for any dependencies before renaming a column. Okay, that's it for now. See you next time. Hello and welcome to the Alter Table Challenges. In this set of challenges, you'll be altering some existing tables. Let's take a look at the first challenge. For the first challenge, you are to add a new column called termination date onto the hcm.employees table. Give this new column a data type of date. Coming up is the hint. So you can use an alter table add statement. Okay, moving to the second challenge. Write two SQL statements to change the data type of the first name and last name columns to varchar 60 in the oes.customers table. Coming up is the hint. Use two alter table modify statements, one for each column. So with alter table modify, you need to do one column at a time. Okay, so moving to the third challenge. So for this challenge, you are to rename the column called phone to main_phone in the oes.customers table. So coming up are the hints. So the hints for this one are to use an alter table change column statement and use a data type of varchar 26 with the not null constraint for the column definition. Alright, so give those few challenges a go, and coming up next, we'll be going through the solutions. Okay, welcome to the solutions to the alter table challenges. So for the first challenge, you were to add on a new column called termination date to the HCM.employees table. So this will be the date at which an employee leaves an organization. Okay, so the syntax is just alter table, our table name, and then we have the keyword add. We give the column name we want to add and its data type. So we just have add termination date of data type date. So let's highlight that and click on the selected portion button. Okay, so that has now added that new column to the table. So if we select from the HCM.employees table and we scroll to the end, we can see we have our new column termination date, and at the moment we just have a null on every row for this column. Okay, so let's go to the second challenge. So for the second challenge, you were to change the data type of the first name and last name columns to varchar 60 in the OES.customers table. So this time we're going to use an alter table modify statement. So we have alter table OES.customers, then we have the keyword modify, then we give the column that we want to modify. So we have our first column is going to be first name, and we're going to change the first name column to a data type of varchar 60. So we just write varchar 60. And note that with the modify statement, we can only modify one column at a time, and hence why we need a separate alter table modify statement to change the last name's column definition. Okay, so I'm going to highlight both those statements and click on selected portion. Okay, so that has now modified those two columns. Okay, so if we have a look at the OES schema and then go to tables, customers, columns, and then we click on first name. So now we can see here for the definition, it's saying varchar 60, and click on last name. Now it's the same, also varchar 60. So we can see that this has worked. Okay, so let's move to the third challenge. So for the third challenge, you were to change the column name from phone to main phone in the OES.customers table. So for this one, we're going to use the alter table change column statement. So we have alter table OES.customers, the keywords change column, and then we give the old column name, which is just phone. We have a space, and then we have our new column name, which we're going to call main_phone. And for this one, we need to specify the data type of the column, even if we don't change the data type. And this is the case here. We're not changing the data type of the column, but we still need to specify it. So if I click on phone here, we can see that the phone column has a data type of varchar 26. But what this doesn't show here is that the phone column also has a not null constraint. To see that, we can right click on customers table and then go copy to clipboard, and then from the items we can select create statement. So that's copied the create statement for the customers table to the clipboard. And then I'm going to open up a new SQL worksheet. So I'm going to click on this SQL Plus button, which is create a new SQL tab. And then I'm just going to right click in the sheet and go paste. So that's going to paste the create table statement from the clipboard. And if we have a look at the phone column, it has the data type varchar 26, but it also has a not null constraint on it. So we're going to copy all of that, and that's what we're going to use as our column definition down here. Okay, so we just write varchar 26 not null. Okay, so if we highlight that and click on executed portion button. Okay, so now that should have changed the data type. So if we refresh the table, so refresh all, and if we click on main phone, so now it's called main phone instead of phone, and it has the data type, same as before. Alright, so that's it for the lecture. See you next time. Hello everyone, and welcome to the drop table statement lecture. Let's get started. The drop table statement can be used to completely remove a table from the database. Therefore, drop table will delete all the rows as well as the table structure itself. Let's take a look at the syntax. So we have the keywords drop table, then we give the schema name dot table name for the table that we want to completely remove from the database. Okay, let's take a look at an example. So in this example we have drop table dbo.products. So we're dropping a table called products in a schema called dbo. Note, when a table is dropped, then all the associated indexes and constraints on that table are also dropped. Okay, let's now go to MySQL Workbench and go for a demo. Okay, so if you want to follow along with this demo, then open up the drop table demo file attached as a resource link to this lecture. So first of all, we're going to select from the dbo.dept table. And we created this table in a previous challenge along with the dbo.emp table. If you haven't completed those challenges and you haven't got these tables created, then there's another file attached to this resource link called create dept and emp tables, and so you can go ahead and open that one first, execute the file to create the tables, and then you can carry on with this demo here where we will drop one of these tables. Okay, so let's select from the dbo.dept table. So I'm going to click in here, click on the execute I button. Okay, so we have our table here and we've got 28 rows in the table. And if we look at the child table, which was the dbo.emp table, so we'll execute that one, and we've got one row in the emp table. Okay, let's now try to remove the dept table. So I will click in this statement, execute it. Okay, so we've got an error message, and the error message is cannot drop table dept referenced by a foreign key constraint, and then it gives the name of the foreign key, which is fkemp dept id on table emp. So recall that we have a foreign key on the emp table which references to the dept table, and that foreign key was on the department ID of the emp table. So what it's telling us is basically we've got this dependency on the dept table as the emp table is dependent on the dept table. So one way of getting around this is to first drop the child table and then we can drop the parent table. So we could do drop table emp followed by drop table dept, and that would work. The other way is if we wanted to just drop the dept table and not the emp table, would be to first drop the constraint on the emp table, which is referencing back to the dept table. And that way the tables are independent of each other and we can go ahead and drop the dept table. And we have this summary here which explains it further, which is we need to either drop the child table first, i.e. the dbo.emp table, or the foreign key constraint on the child table that is referencing to the parent table, which is dbo.dept. Okay, so because we only want to drop the dept table, let's go ahead and remove that foreign key constraint on the child table. So to remove the foreign key, we have alter table, dbo.emp, and then we have drop constraint. So we can also use the drop keyword to drop different things, not just tables. We can use it to drop constraints, views, stored procedures, etc. So anyway, we've got drop constraint, and then we give the constraint name, which we got from down here. Okay, so let's click in here and execute it. Okay, so this is telling us that it has been successful, so we've dropped that constraint. So now we can go ahead and we can drop the dbo.dept table. So I'll click in here, execute I, and there we go, the table has dropped. So if we now try and select from the table, we will get an error message because it no longer exists. So if we click there, so now we get the error, which is table dbo.dept does not exist. And if we try to drop the table again, we're going to get another error message that the table no longer exists as well. So if we try drop the same table again, we get unknown table dbo.dept. Okay, so a way around this is that we can use the if exists option to only drop a table if it currently exists. So the syntax for this is going to be drop table if exists and then our table name. So if we click in here and execute it, so now we just get this exclamation mark and we have a warning, but not an error message as such. So it hasn't actually done anything. It first of all checked if the table exists. If it did exist, then it would drop the table. And if it didn't exist, which in this case it does not exist anymore, then it takes no action. To illustrate where this might be useful is if we have more than one statement and we want to carry on running the statements. So we don't want it to just get to this drop table statement and then it produces an error if the table does not exist. So imagine if we had a select statement after the drop table statement. So we could have select star from dbo.emp. Okay, so if we didn't have if exists, so if we just removed that one and we highlight both the statements and we execute the selected portion, which is these two statements. So we get just that drop table error message and it doesn't carry on to execute the second statement. But if we put back in that if exists, so if we have that if exists operation, then it's going to carry on to the next statement. So if we highlight both of these, execute the selected portion, so now we can see that we get the second statement returned. So this one here didn't do anything and now it moves on to the second statement. So if exists is quite useful if we have a batch of statements and we want to make sure that we just carry on to the next statement if the table no longer exists. So we'll just remove this one. Alright, so that's it for the drop table lecture. See you next time. Hello everyone and welcome to this lecture on transactions in MySQL. Let's get started. A transaction is a single unit of work, sometimes made up of multiple operations. For example, a transaction could consist of one or more SQL statements which change data in a table. In order to maintain consistency in a database, a transaction should have 4 properties as given by the ACID acronym. So the ACID acronym stands for atomic, consistency, isolation, and durability. Okay, let's cover the first one. A transaction should be atomic. This means that either all the statements within the transaction are successfully saved, or none of them are saved. You do not want some statements to succeed and some that fail. Instead, it should be all or nothing. And note that when a change is saved to the database, we say that it has been committed to the database. Let's move to the next property. A transaction should be consistent. This means that a transaction should move the database from one consistent state to another. All data remains valid according to defined rules such as constraints. A transaction should be isolated. This means that each transaction occurs in isolation. In other words, no transaction will be affected by any other transaction. When a transaction is isolated, then multiple transactions can occur independently of each other without any interference. A good example of this is to think about 2 customers buying the same product from a website. There are 10 units of the product left in stock. The customer who clicks the buy button first purchases 8 units of the product in a transaction. This transaction gets committed, and only after it gets committed does the second customer's transaction go through. Therefore, the second customer is limited to only buying up to 2 units of the product, as that's all that is left remaining in stock after the first customer's transaction. So isolation ensures that both these transactions occur independently of each other, and that the second customer's transaction is only completed after the first customer's transaction has completed. This ensures that we don't end up selling more units than we have in stock. Okay, let's look at the final property. And finally, a transaction should be durable. This means that the changes made by a successful transaction are committed to the database and will persist even if a system failure event occurs. For example, if a power failure event were to occur. So let's say you had some bank transaction where you were changing money from one account to the other, and there was some system failure event to happen. You wouldn't want to be in a situation where you actually lost money. You'd either want it in one account or the other. Okay, so a good transaction should possess all four of the ACID properties. Let's now go through some notes about how MySQL deals with transactions. A transaction is successful if no errors are raised. In most cases, a transaction will be doing some data modifications. And if there are no errors, then the changes are committed to the database. If a transaction encounters errors, then it must be cancelled or rolled back. Therefore, no data modifications are committed in this scenario. By default, MySQL auto-commits every successful SQL statement. This means that if you successfully execute a statement, such as an insert statement, then it will be automatically committed to the database. The same is true for other statements such as update, delete, create table, alter table statements. However, sometimes we might want to have more control over the process, and one way we can achieve this is by doing an explicit transaction. Let's go through that. We can define an explicit transaction by using a start transaction statement. This can then be ended with either a commit or a rollback statement. A commit statement will save the changes, whereas a rollback statement will undo the changes. It is common to put an explicit transaction within a stored procedure, and we'll be looking at stored procedures in the next lecture, but first, let's go through an example where we might want to use an explicit transaction. Okay, up top here we have a table of products, and we're showing a few products in the products table. And down below we have a table called inventories, and this is a child table to the products table. This relationship is enforced by a foreign key on the product ID column in the OES.inventories table. So this foreign key ensures that the product IDs in the inventories table are valid product IDs that exist in the products table. Alright, so we might get one product which exists at multiple warehouses as given by the inventories table. Let's say we wanted to add the following product. So here we're adding a product called PBX printer to the products table. And note that the product ID column has the auto increment property on it. Therefore the product ID value is auto generated, and in this scenario it gets a value of 80 generated. Okay, so after we have updated the products table, we also want to update the inventories table with the following two rows. So we have this new product in stock at a couple of warehouses. So we have 100 units of the PBX printer at warehouse 1, and we have 35 units of the PBX printer at warehouse 4. What we want to do in this case is we want to capture the last product ID value generated by the auto increment property when we do the insert statement to the parent table for PBX printer. So we want to get this value here, 80, and then insert it for our new rows to the child table. Moreover, we want to do all this in one transaction because we either want the whole thing to work or none of it to work. The last thing we want would be for this to partially work. In other words, we don't want to be left with one table with new data in it, but not the other. Okay, let's now look at how we can achieve this in a transaction. So first we're going to start a new transaction. And we do that by writing start transaction, then we have our semicolon. Next, we insert a new row for a new product into the products table. And in this case, the primary key column is called product ID. And as we saw earlier, the product ID has an auto increment property on it. And therefore the product ID values get automatically populated. And therefore we don't need to specify product ID in the insert statement. Okay, so we insert this new product, and it automatically gets given a new product ID. Next, we're going to create a variable called new product ID that will store the newly generated product ID. Okay, let's show that. So to create a variable in MySQL, we first write the keyword set, and then we give the variable a name, and variables in MySQL always need to start with the @ symbol. So in this case, we are naming this variable at new product ID, and then we need to set the variable equal to a value. In this case, we are setting this variable equal to a value produced by this last insert ID function. So this last insert ID, we have a set of empty parentheses after it, and this returns the auto increment ID of the last row that has been inserted or updated in a table. So in this scenario, the function is going to return the product ID of this row here for PBX printer. So a variable can be thought of as a container to store some value in it. So let's say that the auto increment value for the PBX printer that gets generated was a value of 80. Then last insert ID is going to get that value of 80, and that's what's going to return. And we're going to store it in our variable here, new product ID. Okay, so next we're going to insert the inventory information for the new product. So here we are inserting 2 rows into the inventories table, and notice that we just pass in our new product ID variable for the product ID column. The final step is to commit the changes to the database. So to commit the transaction, we just have the keyword commit, then we have a semicolon. The key thing to remember from all this is that the commit will only happen if both insert statements are successful, and this is because we have put both insert statements within one transaction. If you want to further review transactions, then I've put a similar transaction to this one in an example SQL file, which is attached to this lecture. Okay, so that's it for the lecture. See you in the next one. Hello and welcome to the lecture on stored procedures in MySQL. Let's get straight to it. A stored procedure is simply some SQL code that is saved in the database which can be executed, i.e. called. When a stored procedure is called, the SQL statements contained within the procedure are executed. Some stored procedures might return a query result based on some input parameters that we provide to it, or a stored procedure might be used to update data in one or more tables. So there are a whole range of things that we can do with stored procedures. Often stored procedures will contain a batch of SQL statements which are treated as a logical unit. So this is where the SQL statements would be put into an explicit transaction. A stored procedure can be defined to accept input and output parameters. And there's actually a third type of parameter called an in-out parameter, which is a combination of both an input and an output parameter. Alright, so input parameters are the most commonly used. This is where we pass some value or values into the stored procedure. This is like how we specify an argument when using a function. On the other hand, an output parameter returns some value from the procedure after it has executed, and we can do things with that value. An input parameter, we pass in some values and then we get a query result back. Okay, let's look at the basic syntax for a stored procedure. So to create a stored procedure, we write the keywords create procedure, and then we give the procedure a name, and then within parentheses, we first give the parameter type, so this is whether it's in, out, or in, out, and then we give the parameter a name, and then we specify the data type for the parameter. And if we have more than one parameter, we separate them with commas. Okay, so we use a closed parenthesis to close off the parameter definitions. Then we have the keyword begin, and then we have our procedure body, which is one or more SQL statements. And then we have the keyword end to close off the code block. And another thing we need to do when creating a procedure is to change the MySQL Workbench statement delimiter from a semicolon to something else while the procedure is being defined. So this takes a bit of explaining, so let's take a look at an example. Okay, so let's go through the stored procedure definition line by line. So on the first line here we have the keyword delimiter, and this is followed by 2 forward slashes. So what this does is that it changes the delimiter from a semicolon to 2 forward slashes in MySQL Workbench. Okay, so by default, MySQL Workbench recognizes the semicolon character as a delimiter and this delimits, i.e. separates, each SQL statement so that each SQL statement is executed separately. However, a stored procedure can consist of one or more SQL statements separated by semicolons. Therefore, if you use MySQL Workbench to define a stored procedure that contains semicolons, then MySQL Workbench will not treat the whole stored procedure as a single unit of work, but instead it'll hit the first semicolon, then think that's the end of the stored procedure. But what we really want is for MySQL Workbench to go all the way to the end, to just after the end keyword, and therefore treat the stored procedure as a whole. Therefore, we must temporarily redefine the delimiter to some other character other than a semicolon, so that we can pass the whole body of the stored procedure to the server as a whole. To do this, we write the keyword delimiter at the start here, and this is followed by the delimiter character. Now, the delimiter character may consist of a single character or multiple characters. For example, in this case, we are using 2 forward slashes, which is a common convention to use. Okay, so now we can start our create procedure statement. So in this case, we have create procedure. We give the procedure a name. So in this case, it's called get employees by city, and it's been created within the HCM schema. And then on the next line, we have within parentheses our parameters. So in this one, we just have one parameter called param city, and it's an input parameter. So before the parameter name, we write the keyword in. We have the parameter name, and then we have the parameter data type. So we're giving this parameter a data type of varchar 50. Okay, so we've just defined one parameter for this stored procedure. Okay, so on the next line, we have the keyword begin. So this indicates the start of the code block for the stored procedure. And this is followed by one or more select statements. And in this case, it's a very simple stored procedure as we only have one select statement. So in our select statement, we are selecting some columns from the employees table. And in the where clause, we have where city equals param city. So what this query is going to do is it's going to select the employees where the city column is equal to the parameter param city value. So the param city value is what will be passed in by the user when they're calling the stored procedure. And just note that oftentimes the parameter name will be given the same name as a column name. But in this introductory example, I've called the parameter param city to make it a bit easier to distinguish from the city column. Also, notice that we need to finish our select statements with a semicolon. So this semicolon does not get recognized as a delimiter by MySQL Workbench because we have changed the statement delimiter to 2 forward slashes up here. This enables the semicolon delimiters used in the procedure body to be passed through to the server rather than being interpreted by MySQL Workbench. Alright, so then we have the keyword end to end the code block, followed by 2 forward slashes. So the 2 forward slashes is what we are using as the delimiter that MySQL Workbench will recognize as a delimiter, indicating the end of the stored procedure. And then finally, we are setting the delimiter for MySQL Workbench back to the semicolon by writing the keyword delimiter followed by the semicolon character. Don't worry if this all seems a bit confusing. In just a moment, we will go through a demo in MySQL Workbench where it should make a bit more sense. Before we do that, let's just cover the syntax for executing a stored procedure. To execute a stored procedure, we just write the keyword call, and then we give the procedure name, and then within parentheses, we specify the parameter values that we want to pass into the stored procedure. And if a particular parameter is expecting a date or a string data type, then we need to put that in single quotation marks. For example, if we were to execute the get employees by city stored procedure, we would write the following. So we just have call, the procedure name, get employees by city, and then we pass in the parameters. So this one only has one parameter, So we just write the string value for the city we want to filter on. In this case, the stored procedure will return all the employees from the Seattle city. Okay, let's now switch to MySQL Workbench and go for another example of a stored procedure. Okay, so if you want to follow along with the demo, as usual, it's attached as a resource to this lecture. So here I've got a query which returns the employees from the finance department. So let's just click in here and have a look at it. Okay, so all this query is doing is it's joining the employees table to the departments table, and then we are filtering on the departments table department name where it's equal to finance, and we get all the employees in the finance department returned. So let's say we wanted to put this into a stored procedure, and the reason why we might want to do this is so that we don't have to write this query every time we want to search for employees in a particular department. And we could also share this stored procedure with other people, and they wouldn't have to write this query each time they wanted to do this type of analysis. Okay, so here we are creating a stored procedure where a user passes in a department name as an input parameter, and the procedure returns all the employees in that department. So first of all, we set the delimiter for MySQL Workbench to 2//, and then we can start our procedure. So we have create procedure, we give the procedure a name, so I'm calling it get employees by department. We're creating it in the HCM schema, and then within parentheses we specify our parameter definitions separated by commas. In this case we've just got one parameter, so it's called department underscore name. So before the parameter name we specify the parameter type, so this is going to be an input parameter, so we write the keyword in, and input is where someone will need to input the parameter value when calling the stored procedure. So we also need to give the parameter a data type, and this is going to be a varchar 50 data type. And I've just given it a data type of varchar 50 to match the data type of the department name column in the departments table. Alright, so on the next line we have the keyword begin to start the code block. Then we have one or more select statements. So in this case we just have one select statement. So we are selecting some columns, we're joining up the employees table and the departments table, and we're doing an inner join, so we're only going to return the employees who do actually belong to a department. And after our join we have our filter, so we have where the department name equals department name. So this seems a little bit confusing, but what this is saying is it's saying where the departments table department name column is equal to the input parameter. So our input parameter in this case has been given the same name as the column name, but MySQL is smart enough to work out that this is the same as this up here. So the user will pass in a department name, and then the query will then filter for that department name down here. Okay, so now we have our semicolon, and this semicolon gets sent to the server, and then we have the keyword end, and this ends the code block, and then we have our 2//, which MySQL Workbench, which is our SQL client, recognizes as a statement delimiter. So this is the end of the create stored procedure. And finally, after all that, we change the default delimiter back to a semicolon. So after running this line here, again, MySQL will go back to normal, where it will recognize the statement delimiter as being a semicolon. Okay, so let's just highlight all of that and click on the execute selected portion button. Okay, so that has created the stored procedure. So if we go across to our schema navigator and right click on HCM schema, go refresh all, and now under stored procedures we see our new get employees by department stored procedure. So to execute this stored procedure, which is to call it, we just write the keyword call, we give the stored procedure name, and then we give our parameter values in a comma delimited list. In this case, we just have one parameter for the department. So to get all the employees in the finance department, we're going to write finance in single quotes as it's a string. Okay, so let's click in here and execute it. So now we get all the employees from the finance department. And if we were to get all the employees from the sales department, we would just pass in the string value sales. If we click in here, execute it, and now we get all the employees in the sales department. So this stored procedure has saved us from writing that SQL all over again. Instead, we've just packaged it up into a stored procedure, and we can just change the parameter values to get back a different result. Alright, so that's it for stored procedures. See you next time. Welcome back everyone. In this lecture, we're going to be covering unique constraints. Let's get straight to it. The unique constraint is a type of data integrity constraint. A unique constraint ensures that the column specified in the constraint can only have unique values. If multiple columns are specified in the constraint, then only unique combinations of the column values are allowed. The unique constraint is similar to a primary key constraint, however, there are some important differences. And let's now go over what those differences are. So with a primary key, a single table can only have one primary key constraint, whereas a single table can have multiple unique constraints. A primary key ensures that the values are both unique and not null in the primary key column or columns, whereas a unique constraint ensures that the values are unique, however, nulls are allowed. But in saying that, you can have a column where you apply both a unique constraint and a not null constraint, in effect mimicking a primary key constraint. Okay, so one other thing that a primary key has in common with a unique constraint is that both automatically create a corresponding unique index. A unique index essentially enforces the uniqueness rule, and it can also speed up searches on the column. Alright, let's now go through an example of where we might use a unique constraint. So here we have a table of products, and the product ID is the primary key. So product ID is guaranteed to have unique non-null values, since it has a primary key constraint on it. Let's say that we also wanted to ensure that the product name column could only have unique values. We cannot add another primary key constraint because a table can only have one primary key on it. However, we can add a unique constraint on the product name column. We can define constraints in either a create table statement or an alter table statement. In this case, we already have an existing table, and therefore we will use an alter table statement to add on this new unique constraint. So the syntax is alter table, and then we give the table name, and then we have add constraint, we give the constraint name, then we have the keyword unique for the unique constraint, and then within parentheses we specify the column or columns that we want to apply the unique constraint to. So in this example, we could write the following. So this will add a unique constraint called UK products product name onto the product name column in the dbo.products table. So for unique constraints, I always like to start them with the abbreviation UK, short for unique key. An alternative to using a unique constraint is to just use a unique index. A unique index does the exact same thing as a unique constraint, and as previously mentioned, when we create a unique constraint, it automatically creates a corresponding unique index for us. Okay, let's now go through a quick challenge. In this challenge, you are to use an alter table statement to add a unique constraint to the department name column in the hcm.departments table. So pause the video and give this challenge a go. Okay, let's now go through the solution in MySQL Workbench. Okay, so if you want to follow along with the demo, you can just download the SQL file attached to this lecture. So first of all, we're going to have a look at the hcm.departments table. And you can see that we have department ID, department name, and location ID. So our challenge was to add a unique constraint to the department name column to make sure that in the future no one added on duplicates into the department name column. So before actually adding on a unique constraint, sometimes what I like to do is to check if the column does have unique values. So if it doesn't already have unique values, we'd have to remove the duplicates before we can actually put on a unique constraint. Okay, so one way of doing that is to do select count all the rows, so count asterisk. So I'm calling that total count, and then we've got comma, and then we're doing count distinct department name, and I'm calling this unique value count. So if we click in here and execute it, so because the total number of rows is equal to the unique value count, this means that we have unique values. So if these two numbers were different, then this would mean that we didn't have unique values in the column. Okay, so the solution was alter table hcm.departments. Then we have the keywords add constraint. We give the constraint a name. We have the keyword unique for unique constraint. Then we pass in the column that we want to apply the unique constraint to. So we have department name within parentheses. Okay, so I'm going to highlight that. Click on the selected portion button, and that has altered the table and added on that constraint. So one way of looking at the constraint to check it has been added is to query the information schema views. So we're joining up a couple of the views in the information schema, and then we're filtering in the where clause where the schema name is HCM and the table name is departments. So I'm going to click in here and execute that one. So now we can see all the constraints on the departments table, and we have a primary key, a foreign key, and we also have our newly added unique constraint on the department name column. Okay, so if we test it out, so let's try to insert a duplicate row and see what happens. Okay, so we have insert into our departments table, and then we give our columns, and then we're trying to insert a department called administration, but we already have a department called administration in the table. So let's highlight that, execute it, and we get an error message down here which said that duplicate entry administration for key departments.uk departments department name. So this is just telling us that we've got a unique constraint on this column, and therefore we cannot insert duplicate values into the column. Alright, that's it for now. See you next time. Hello everyone, and welcome to the check constraints lecture. Let's get straight to it. A check constraint is a type of data integrity constraint. A check constraint can be applied to a column and checks that each value in the column meets a certain condition. A check constraint cannot refer to a column from another table. Also, a check constraint cannot contain a subquery. Okay, let's have a look at the syntax for a check constraint. So just like all the other types of data integrity constraints, we can define a check constraint either in the create table statement or in an alter table statement. Given here is the syntax for how we can add a check constraint onto a column in an existing table by using an alter table statement. So we have the keywords alter table, we give the table name, then we have the keywords add constraint, we give the constraint a name, and then we have the keyword check for check constraint, and then within parentheses we specify the column name and the condition. Okay, so let's look at an example. So here we are defining a check constraint on the quantity column in a table called order details. And the condition we have is that the quantity must be greater than 0. Therefore, this check constraint ensures that the column called quantity will always have a value greater than 0. And note that this particular check constraint still allows nulls to be inserted into the quantity column. If we wanted to prevent nulls as well, then we could use a not null constraint in addition to the check constraint. One other thing about check constraints in MySQL is that the constraint name is optional. So if we decide not to give the check constraint a name, so if we left the name out, then MySQL would have given it a system-generated name. However, I always like to give my constraints a more meaningful name. Okay, let's take a look at another example. Okay, so here we have a table of products, and let's say we want to put a check constraint on this column called color. And we can do that by using the in operator in the check condition. Let's take a look at the alter table statement. So in this example, we have added a check constraint onto the existing dbo.products table, and we're calling the constraint check products color. And what this check constraint is doing is it's checking that this column called color can only be one of these possible values. So it can only be red, blue, yellow, black, or white. So we would get an error message if we tried to insert any other value into the color column. And note that in this example we have two sets of parentheses. So the innermost set of parentheses is for the in condition, and the outer set of parentheses is for the check condition. So we always need to put the full check condition within parentheses. Okay, let's now go through a quick challenge. Use an alter table statement to add a check constraint on the salary column in the HCM.employees table to ensure that salary is greater than or equal to 0. Okay, so pause the video and give this challenge a go. Alright, let's now switch to MySQL Workbench and go through the solution to this challenge. Okay, so this challenge is pretty straightforward. It's just alter table, we give the table name, then we have add constraint, and optionally we can give the constraint a name, then we have the keyword check, then within parentheses we specify our condition, which in this case is that salary, so we have salary is greater than or equal to 0. And if we click in here, execute it. So now with this check constraint in place, we can only insert new employees if they have a salary that is greater than or equal to 0. Alright, so that's it for now. See you next time. Welcome back everyone. In this lecture, we're going to be introducing the topic of data normalization and why we normalize data. Okay, let's get started. Data normalization was first proposed by Ted Codd in 1970 and has become the cornerstone of relational database design. Mr. Codd was a computer scientist who, while working for IBM in 1970, wrote a seminal paper called A Relational Model of Data for Large Shared Data Banks. So this paper kicked off the whole relational database design industry. Okay, so data normalization is a process of organizing attributes into tables to minimize data redundancy, i.e. unnecessary duplication of data. And we'll be seeing later on that data normalization rules tend to increase some duplication of data, but it does not introduce data redundancy, which is unnecessary data duplication. For instance, we might copy a primary key from a parent table and use it as a foreign key in a child table. We are duplicating data, but this is a necessary duplication of data in order to relate a parent table to a child table. Data normalization typically involves breaking larger tables into smaller, less redundant tables and defining relationships between them. These relationships are generally the primary key to foreign key relationship, which enforces data integrity. So you might be wondering why Ted Codd named this process normalization. So he was asked this question in an interview, and his answer was, I called it normalization because then President Nixon was talking a lot about normalizing relations with China. I figured that if he could normalize relations, so could I. So often in international diplomacy, the phrase normalizing relations will be used when two countries try to have a friendly relationship again after they have had a war or a disagreement. However, in database terminology, a relation is a set of tuples which SQL represents by a table. So we have a clever play on words here by calling this process normalization. Okay, let's go over why we normalize data. So the first reason is that it eliminates the potential for update, insertion, and deletion anomalies to occur. These data anomalies or inconsistencies are what we want to avoid. Shortly, we will be going through examples of these different types of anomalies and how they can occur. Okay, so another reason for normalizing data is that it reduces the need for restructuring data as new types of data are introduced to the database. Also, it makes the data more informative to users. Alright, let's go over the data change anomalies. So an update anomaly occurs where one or more instances of duplicated data is updated, but not all of it is. An example is if an employee changes their email address, and this is updated in one row, but there are still some other rows which have their old email address. So in this case you'd get a data inconsistency occurring. Note that some textbooks use the term modification anomalies to describe this type of anomaly. Also, they will use update anomalies as a general term to describe all types of anomalies. But in this case here, I'm using update anomaly in a more specific sense. Okay, with that aside, let's take a look at an example of an update anomaly. In this example, we have an instructors table and a classes table. Note that the classes table has repeated information about each class. The class name, contact, and cost columns are repeated for each instructor who takes the class. In other words, every time a new class is entered into the classes table, we have to repeat the class name, the contact phone number, and the cost. Over time, having to insert repeated information inevitably leads to some rows having inconsistent values. And we can see that this has happened for the Intro to SQL class. So notice that the contact number for the Intro to SQL class ends in 80 for the first two rows. However, on the last row here we have a different contact number which ends in 81 for the Intro to SQL class. So which of these contact numbers is correct? Well, we don't really know. All we know is that we have inconsistent data that would require further investigation and fixing. Okay, let's now go through insertion anomalies. An insertion anomaly occurs when particular attributes cannot be inserted into a table without other attributes also being present. In practice, this occurs when you are prevented from inserting data into a table as you do not have a complete key value. An example is if you had an employees table which also held all the department attributes. You could not add a new department until it had at least one employee. Alright, let's go for an example using our instructor and classes tables. So in this example we have a composite primary key on the classes table, which is the combination of the instructor ID and the class ID attributes. So this composite primary key ensures that these two columns have unique combinations of values and no nulls are allowed in either of the two columns. Alright. So let's say we have this scenario where we want to add a new class to the classes table. So this new class is for Advanced Excel. However, notice that this class does not have any instructor assigned to teach the class yet. Therefore, we have a null for instructor ID, and this means that we cannot insert this row because instructor ID is part of the primary key, and of course we cannot insert nulls into a primary key. In other words, we have no way of recording information about a class before an instructor starts teaching it. Okay, let's take a look at one more type of data anomaly, which is the deletion anomaly. A deletion anomaly occurs when certain attributes are lost because of the deletion of other attributes. An example is if you had a threat and species table, which also held all the park attributes. Imagine that there was only one species at a particular park. Let's say Golden Park. This species eventually goes extinct and therefore this species row is deleted from the table. However, this means we lose the information that Golden Park exists. In other words, an attribute of the threatened species was that it existed at Golden Park. Golden Park did not have any other threatened species, so when we deleted the row, we also lost the fact that this park exists. Note, having more than one entity in a table is a bad thing. So in this example, we have two entities mixed into one table, which are species and parks. So in general, we want one entity in one table. Okay, let's take a look at another deletion anomaly by going back to our instructor classes example once more. Okay, so let's say that Jillian Singh, who is instructor ID number 3, decides to leave the organization. Therefore, we delete her record from the instructors table, as well as any classes that she teaches in the classes table. However, by deleting information about the instructor, we have inadvertently lost information about the Advanced Web Design class. And this is because Jillian was the only instructor for the Advanced Web Design class, and therefore by deleting her record, we have lost important information about the class, such as the class contact and class cost. This would then have to be sourced and entered all over again once the school found a replacement for Jillian. Okay, so before we finish the lecture, let's quickly show how we can structure this data so that it is normalized and we don't have any chance for these data anomalies to occur. So in this scenario, what we first need to do is work out the type of relationship we have between these two entities, which are instructors and classes. In this case, there is a many-to-many relationship between instructors and classes, and this is because at this school, one instructor can teach multiple different classes, and one class can be taught by multiple different instructors. Because of this many-to-many relationship, this means that we need to have what's called an association table, which in this case will just be the instructor ID and the class ID. Okay, let's show that. So here is the normalized structure, and we have an association table in the middle here, which I've called instructor classes. And this is a dedicated table showing all the different combinations for instructor ID and class ID. In other words, which instructors teach which classes. On either side of the association table, we have two parent tables. So we have a parent table for instructors and a parent table for classes. And notice now that each row in the classes table is a unique class. So we don't have any repeated information like we had before. For our keys, we have a composite primary key on the association table, and we also have two foreign keys on the association table, with each foreign key referencing back to the primary key of their respective parent table. This structure prevents anomalies from occurring. For instance, if we were to change the contact phone number for the Intro to SQL class, we only need to change it in one place on one row. Therefore, we don't get any update anomalies occurring. Likewise, if we wanted to add a new class, but we did not yet have any instructor teaching that class, then we are free to do so, as the classes table just has classes attributes in it. So we don't get any insertion anomalies happening like we did before. Also, no deletion anomalies can happen either. So for example, if there is only one instructor teaching a class, and that instructor decides to leave the school, then we can remove them without losing information about the class. So going back to the example of Jillian Singh, if she was to leave the school now, then we can remove her from the instructors table and from the instructor classes association table, but we can now retain the information that there is still a class called Advanced Web Design, even though after Jillian leaves, we'll have no one teaching it for a period of time. Okay, so these tables would look like the following in a typical entity relationship diagram. Here we have the same tables, but we are just showing the table name and column headers in each box. So each box is an entity, and the primary key columns are underlined. The crow's feet here and here represent the many side of the relationship, and these are columns which have foreign keys, and the vertical bars are on the one side of the relationship, and that is for the parent record. Alright. So in this lecture we introduced the topic of data normalization, and then we covered the different types of data anomalies that can occur if we don't normalize data. In later lectures, we will cover the formal process of data normalization and the normal forms. Alright, that's it for now. See you next time. Hello and welcome to this lecture on functional dependencies. A prerequisite for understanding data normalization is to first be able to understand and identify functional dependencies in our data. So, what is a functional dependency? A functional dependency is a type of relationship that occurs when an attribute, or a set of attributes, uniquely determines another attribute. For example, let's say we have two attributes, x and y. if attribute X functionally determines attribute Y, then every value of X determines exactly one value of Y. This is denoted as X arrow Y. Okay, let's take a look at some real examples. So here we have a table with student ID and first name. Each student ID number uniquely identifies each student's first name. Therefore, we have the functional dependency of student ID functionally determines first name. And this is because each student ID value is associated with exactly one first name value. In fact, if the attribute on the left-hand side of the arrow, so in this case it would be student ID, if that's unique, then that means that it will functionally determine all other attributes in the table. Alright, let's now look at the reverse relationship. Does first name functionally determine student ID? You might want to pause the video and have a think about this question. Okay, so the answer is no. First name does not functionally determine student ID because we might get many different students with the same first name. For example, we have two students with the first name Angela. The name Angela is associated with two different student ID values, values 4 and 5. In other words, the first name attribute does not uniquely determine student ID. You might be thinking, what about if there was only one Angela in the table? For example, so now we don't have any students with the same first name. In this scenario, we can know with certainty what each student's student ID is just by looking up their first name. However, functional dependencies must always hold true. And since we know that it is possible to have students with the same first name, therefore we know that first name cannot be relied upon to uniquely determine the student ID. Okay, let's go through another example. Here we have a table of conference room numbers, and we have room capacity, which is the maximum number of people that each room can hold. We also have a column for the building name. So for instance, we've got the Grand Star building, and that has two conference rooms, 101 and 102, with room capacities of 300 and 200 respectively. Alright, so can you see any functional dependencies between any of these attributes? You might want to pause the video and see if you can find one. Okay, so this was a bit of a tricky question, but there is a functional dependency, and that is the set of attributes building name and conference room functionally determine the room capacity. In other words, we need to know both the building name and the conference room number in order to uniquely determine a single value for the room capacity. At the moment, each conference room has a different number, but it is entirely possible that in the future we could have two conference rooms in different buildings that have the same room number. Therefore, conference room by itself does not functionally determine room capacity, as this is not guaranteed to always hold true. To make this a bit clearer, let's say we add another conference room to the old Western building. So this new conference room has a room number of 11 and a room capacity of 50. However, if we look at the Millennium building, that also has a conference room number of 11, but it's got a different capacity of 75. So now it's clear that we need to know both the building number and the conference room number in order to determine the value for room capacity. We can't just rely on the conference room by itself. Alright, thanks everyone. That's it for the lecture. See you in the next one. Welcome everyone to the functional dependencies exercise. Let's get straight into it. Okay, so here we have a table with 4 columns, A, B, C, and D, and we have 5 rows of data. As a recap, previously we learned that a functional dependency is a type of relationship that occurs when an attribute or a set of attribute uniquely determines another attribute. If attribute X functionally determines attribute Y, then every value of x determines exactly one value of y. With that in mind, see if you can do the following task. Identify all non-trivial functional dependencies in the table above. So pause the video and give that a go. Okay, let's now go through the exercise together. First, we will look at the relationship between attributes A and B, and we will see if A functionally determines B. So in the first row we have A1, B1, and then in row 2 we have A1, B2. So straight away we can see that the value A1 is associated with more than one unique value in column B. Value A1 is associated with both B1 and B2. Therefore, attribute A does not functionally determine attribute B. What about the reverse? Does B functionally determine A? Let's have a look. If we look at the third row, we can see that we've got B2 and A2. So we have the value B2 being associated with more than one A value. So it's associated with A1 and A2. This means that attribute B does not functionally determine attribute A. Okay, let's now have a look if attribute A functionally determines attribute C. So on the first row we have A1, C1, then we have A1, C1 again, then we've got A2, C2, A2, C2, and it's not until the final row that we see a difference here, and we've got A3, C2. And this means that attribute A does indeed functionally determine attribute C. This is because every value of A determines exactly one value of C. In other words, A1 is only associated with C1, A2 is only associated with C2, and A3 is only associated with C2 as well. From this we can also see that attribute C does not functionally determine A, and the reason for this is we have the value C2 being associated with more than one A value. So C2 is associated with both A2 and A3. Moving on, let's see if attribute A functionally determines attribute D. So first row we have A1, D1, then we've got A1, D1 again, A2, D2, A2, D2, and A3, D3. So we can see here that there is a clear matching pattern between A and D, and each distinct value of A is associated with exactly one value of D. Therefore, A functionally determines D. The reverse is also true. D functionally determines A, as we have one-to-one value mapping between D and A. Because attribute D has essentially the same pattern as attribute A, this means that attribute D will also functionally determine attribute C. Alright, let's now look at attribute B and C. Does attribute B functionally determine attribute C? No, it does not. And this is because the value B2 is associated with two different C values, C1 and C2. And we can also see that attribute C does not functionally determine attribute B, as we have value C1 being associated with more than one B value. So C1 associated to both B1 and B2. So no relationship there. Let's take a look if there's a functional dependency between B and D. So there is no functional dependency relationship in either direction for B and D, as value B2 is associated with more than one D value. So it's got D1 and D2. And if we look in the reverse direction, does D functionally determine B? That's also a no, because we've got D1 here associated with more than one B value. Same thing for D2. Let's now look at the combination of attributes. So first question is, should we look at the set A and B and see if it functionally determines attribute C? The answer is no, we don't need to do this, because this would be a trivial functional dependency, because we already know that attribute A functionally determines C. Okay, so what about if we look at attribute B and C as a set? This is an interesting one, because if we look at B and C combined, we can see that we still have a duplicate, and it's on these last two rows here. So we've got B3, C2 on one line, and then on this line we have a repeat, B3, C2. Now, if B and C combined had all unique combinations of values, then it would mean that this combination would automatically functionally determine all other attributes in the table. However, because B and C combined does not have unique combinations of values, we cannot automatically say that it determines the other attributes. Instead, we need to look at each relationship and see if it holds. With that in mind, let's see if BC functionally determines attribute A. So what we can do is we can go straight to the last two rows here, which is where we have our duplicate combinations of B and C, and we can see if these two rows are associated with the same A value. And straight away we can see they're associated with two different A values, A2 and A3. This means that BC combined does not functionally determine A. Also, BC does not functionally determine D, as D has the same pattern as A. So in this case we've got D2 and D3, both associated with the combination B3C2. Okay, hopefully that gave your brain a bit of a workout. If you made any mistakes, don't worry, it can take a bit of time to learn how to identify functional dependencies. I would recommend coming back in an hour or even a day and redoing this exercise to make it stick in your mind. Before ending this lecture, I just want to note that because this was an abstract example, we don't know if these functional dependencies are real or not. In the real world, it is common to find examples where it seems as though there is a pattern that looks like a functional dependency, but we might know that it won't always hold true, as we have more knowledge of what the data actually represents. Previously we saw that with the conference room number to room capacity example. Alright, that's it for this exercise. See you in the next lecture. Welcome back. In this lecture we are going to be covering candidate keys and super keys. Let's get straight into it. So a candidate key is either a single column with unique values or a set of columns that have unique combinations of values. And a set of columns can only be a candidate key if it is irreducible, i.e. it has no unique subset of columns. So in other words, a candidate key is a key where no subset of columns is also a key. A candidate key functionally determines all the other attributes in a table. This is the same as saying that a candidate key uniquely identifies each row in a table. It is worth noting that a candidate key is not a physical design concept, and instead a candidate key is a logical design concept. To ensure that a candidate key remains unique, we can use either a primary key constraint or a unique constraint. So for a given table, then one of the candidate keys would be chosen to have a primary key constraint applied to it, and any other candidate keys in the same table would be given unique constraints. Constraints, such as primary key and unique constraints, are part of the physical design. These are the things we actually do in the database to implement the logical design. More on that in a later lecture. Okay, let's go through some examples. So here we have a table of students, and in this table the student ID attribute is a candidate key because it has unique values, and therefore it functionally determines all the other fields. Okay, let's look at the first name column. Here we can see that first name currently has unique values. However, functional dependencies must always hold true. In this case, first name does not functionally determine all other fields, and this is because in the future we might get more than one student with the same first name. So for example, if we had another Amy come along and enroll as a student, then the first name column would no longer have unique values. Okay, so what about if we combine student ID with first name? So if we look at the combination of student ID and first name, we can see that we have unique combinations of values, and that this will always hold true. However, this is due to the student ID column by itself. Therefore, student ID and first name combined as a set is not a candidate key, as it has a unique subset, which of course is just the student ID column by itself. Recall that a set of attributes can only be a candidate key if it has unique values and if it has no unique subset of attributes. In other words, it cannot be reduced down any further. In this case, we could reduce the attribute set of student ID and first name down to just student ID by itself. Okay, let's look at first name and last name combined. This is not a candidate key because it is not guaranteed to always be unique. So in this case, we might have more than one student with the same first and last name. Now what I'm saying here is a bit different to what you might read in some books on database design. In some books, they would treat this example of first name and last name as a candidate key as it has unique values in the table. However, I believe in a more stricter version of what defines a candidate key, which is that it's only a candidate key if it's guaranteed to remain unique as more data gets added to the table. This makes it more relevant to real-life situations, where we need to consider the future state of the table data and not just the present data. Okay, with that aside, let's include the date of birth attribute in the set of columns. So this is not a candidate key either, because in the future it is possible to get two different students who happen to have the same first and last name and who were born on the same day. You might think this is unlikely, but these sorts of instances do occur, especially if we look at enrollments at a large school or university over a long period of time. Thinking back to when I was at university, I remember an administrator telling me that there were 4 other people at that same university who had the same first and last name as me. Not sure if any of them were born on the same day, but it's always possible. Okay, let's take a look at tax number. The tax number column is a candidate key, as it can be used to uniquely identify each student. Alright, so in this table we have 2 separate candidate keys, and they are student ID and tax number. In SQL, we can only select one of these candidate keys as our primary key, so we can either choose student ID or tax number as the primary key. However, identifying all candidate keys is an important step when normalizing our data structures. In addition, we want to make sure that we have at least a unique constraint or a unique index on each candidate key. We'll be doing all of this in a later lecture. Okay, let's now cover key versus non-key attributes. Key attributes are simply columns used in at least one candidate key. So recall that attributes columns are the same thing, so I'm using them interchangeably here. Non-key attributes are any columns that do not occur as part of any candidate key. Note that key and non-key attributes are also referred to as prime and non-prime attributes. So a prime attribute is the same thing as a key attribute, and non-prime is a non-key attribute. Alright, let's take a look at a table and we will identify which attributes are prime and which ones are non-prime. So here we have a table for student grades. So we have the subject each student took in each year, as well as the grade they got. And at this school, each student takes each subject for a whole year. Okay, so you might want to take a minute to pause the video and see if you can identify which attributes are prime attributes. Alright, let's go through the answer. So prime attributes are key attributes, and these are simply attributes that are part of a candidate key. Candidate key is either an attribute or a minimal set of attributes that can be used to identify each row. If we have a look at student ID, we can see that this is not unique by itself. What if we combine student ID with subject? Well, this is still not unique because we can get the same student taking the same subject but in different years. So for example, student ID 101 has taken calculus more than once. So this student took it in 2020 and 2021. So in other words, we need to include grade year as well to get the candidate key. Therefore, this table has the candidate key, student ID, subject, and grade year combined. This means that all these three columns are prime attributes. This leaves us with the grade attribute, which is a non-prime attribute. Throughout the course, I will often refer to prime and non-prime attributes as being key and non-key attributes respectively. Okay, last of all, let's cover superkeys. So as we have covered, a candidate key is simply an attribute or a set of attributes that have the properties of both uniqueness and irreducibility. On the other hand, a superkey is a set of attributes that have the property of uniqueness but are not necessarily irreducible. In other words, a superkey might have some subset of columns that is also a key. So this means that all candidate keys are superkeys, but most superkeys are not candidate keys. Okay, let's go through the previous table again and identify all superkeys. So in this table we had our candidate key, which was student ID, subject, and grade year combined. All candidate keys are also superkeys, so this is also a superkey as well. However, because a superkey does not necessarily need to be a minimal set of attributes, then this means that each candidate key can be combined with all the other attributes in various combinations to make a superkey. In this case, we just have one other attribute, which is grade. So we have one other superkey, which is all the attributes combined. In this table, it was fairly straightforward to identify all the superkeys, but often a table can have a large number of superkeys. And this is especially true of tables that have a lot of attributes. We're going to have a lot of combinations of columns that will have the property of uniqueness and are therefore superkeys. Okay, that's it for this lecture. See you next time. Okay, let's look at first normal form. So first normal form is, in my opinion at least, the most important normal form. Alright, let's get started. So a table is in first normal form if each column has atomic values that are of the same type and there are no duplicate rows. Atomic values are ones that cannot be broken into smaller parts. Note that technically nulls violate first normal form. This is because nulls are not true values and therefore cannot be of the appropriate type for a column. Some definitions of first normal form exclude the atomic values requirement, and this is because it is not clear as to what makes a value atomic. For example, let's say we had a column with order dates, and we had date values like this one here. So would you say this is an atomic value? Well, one could argue that this is not atomic, because you could always break it down further. In this case, by separating out the year, month, and day parts into separate columns. On the other hand, you could argue that this is atomic because it represents one single thing, which is a point in time when an order was placed. In this case, it is generally best to leave a date value as one column. Okay, let's go over the condition that the values of each column are of the same type. An example of this is if you had a column called phone number, then the values in the phone number column should only contain phone numbers. So this might seem kind of obvious, but there are situations where I've seen this broken. So if there is any value in the column that is not a phone number, then this table does not meet first normal form. Same goes for all the other columns. If you have a column called first name, then it should only contain first name values. When it comes to nulls, in strict terms, nulls violate first normal form because they are not true values. Instead, they are markers for unknowns, and therefore they have no type. In saying that though, in the real world, most database professionals, myself included, will ignore nulls when making a judgment call about whether or not a table meets first normal form. However, even though nulls are integral to the SQL language, nulls can cause problems, and it is generally best to minimize our usage of them where we can. The next condition we have is that there are no duplicate rows. Some definitions of first normal form will say something like, a table is in first normal form if it has a primary key and there are no repeating groups of data. However, the correct terminology to use is candidate key rather than primary key. If a table has no duplicate rows, then this means that the table has at least one candidate key. Recall that a candidate key is either a column with unique values or an irreducible set of columns that have combinations of values that are unique. Identifying candidate keys is something we do to help determine if a table is in first normal form, whereas a primary key is a constraint that we use to enforce a candidate key to always be unique and non-null. A table can have no primary key constraint, but it can still be in first normal form if it has at least one candidate key. The primary key just makes sure that this always holds true as new data is added to the table. Okay, let's take a look at a table that is not in first normal form, and then we will go about normalizing the structure. So this table is not in first normal form for a few different reasons. Note that the problematic cells have been highlighted in red. Okay, so one of the reasons that this table is not in first normal form is because we have a couple of values that are not appropriate for the column they are in. For instance, the email address column has a phone number in it for James Lewis. Also, there is no identifier in the EmpID column for employee Amanda Winter. So Amanda Winter has a null here. So this table fails the condition that the rows of each column must be of the same type. Another problem we have with this table is that we have a duplicate row for employee Judy Robinson. So we can see for the first two rows here that each column has the exact same values. So this also violates first normal form. Yet another problem we have is that for the employee Fred Goodwin, we have multiple emails all in the same cell. So this is not atomic. Instead, Fred has multiple emails given in a comma-delimited list, all in the same field. This is what's called a multi-valued field. So for all of these reasons, this table does not meet the conditions for first normal form. Okay, so one way we could go about fixing this table is to remove the duplicate row, to make sure that each employee only has one row. Then we can also remove the phone number from the email column, and we can ensure that all employees have non-null EmpID values. And for Fred, we can just have one email to make that field atomic. Okay, so let's do that. Okay, so now we have no duplicate rows, all column values are of the same type, and all column values are atomic, i.e. single valued. So this table now meets first normal form. Notice though that we have only selected one of Fred's email addresses. This is not the best because we've actually lost some information about Fred. If we want to be able to store multiple email addresses for each employee whilst maintaining atomic values, then we have a couple of options. One is to simply add on extra columns for each additional email address. So we could have separate columns for email address 1, email address 2, etc. For email addresses, this might be an okay solution because most people are unlikely to have more than a few emails. However, it is generally considered bad practice to add on extra columns with the same type of information. This is because every time we add on a new column to the table, then we have to go back and update any queries that are selecting data from the table. Extra columns also make it more difficult to query and group the data. In fact, many definitions of first normal form will say that a table is only in first normal form if there are no repeating groups. A repeating group is a set of related columns. So if we had multiple columns for each email address, then this would be a repeated group. Confusingly, a repeated group can also refer to a multi-valued field, which is previously what we had with Fred, where we had all his email addresses crammed into one field. And we'll cover this in more detail in another lecture. Okay, so instead of adding on extra columns for each additional email address, the relational database design approach is to create a new child table. So in this case, we would have a child table for email addresses. This is best shown by example. Okay, so now we have split the structure into two tables. One table is our table of employees. This is the parent table, And the other table is the email addresses for each employee. So that's our child table. Now if an employee has multiple email addresses, that's not a problem, as we can just add additional rows to the child table. And the benefit of this is that no information has been lost. So now we have all of Fred's email addresses, each on a new row, and therefore each row has atomic values. So now this structure meets first normal form. Also, we can query these two tables by joining them together based on the emp ID columns. To help ensure that these two tables always meet first normal form, we can add constraints to their tables. So we would make sure that each table has a primary key constraint, and in this situation we would also add on a foreign key constraint onto the emp ID column in the child table. So first, we will put a primary key constraint on the emp ID column in the employees table. Then in the child table, the primary key constraint is a composite one, and this is the combination of emp ID and email address. So this will ensure that we always have unique combinations of values for these two columns. And lastly, we have a foreign key constraint placed on the emp ID column in the child table. And this references back to the emp ID column in the parent employees table. This foreign key constraint ensures that we can only add emp ID values to the child email addresses table if they first exist in the employees parent table. Okay, so these tables are now both fully normalized and meet first normal form, as well as all the other higher normal forms. Alright, that's it for this lecture. See you in the next one. Alright, welcome back everyone. In this lecture, we are going to look at how we can restructure multi-valued and multi-type fields. First of all, let's define what these are. So a multi-valued field is where we have more than one occurrence of the same type of value in a field, and often these occur in a comma-delimited list. So for example, in one field we might have a list of names, say Ellie, Bob, Amy. And a multi-type field is where we have more than one occurrence of different types of values in a field. So for example, we might have a list of names, but we also have their date of birth. So we might have Ellie 1988, Bob 1995, etc. So here we have two types of data all in one field, which are names and birth dates. So columns which have multiple values or multiple types are indicative of poor design. So in general, we don't want to have these types of fields in our database. Instead, we want atomic values. Now to get atomic values for multi-valued fields, typically we need to create a new table to get each value on a separate row. Whereas for multi-type fields, we typically need to separate out the different types of data into columns. Let's go for an example. Here we have a table of power stations and the amount of power they output in different years. The problem with this table is that the power megawatt outputs column does not contain a single value for each power station. In other words, its fields are both multi-valued and multi-type. So it contains multiple types of information as we have the output and the year. And the column is also multi-valued because we have a comma-delimited list of the power output in each year. So we've got 402 in 2015 and 338 megawatts in 2016 for Davies Dam power station. A multi-valued field is also referred to as a repeating group. In this case, we have the power output for each year as a repeating group within this column. So one common attempt to normalize this type of structure is to do the following. Okay, so what we have done now is we have separated out the power outputs into separate columns for each year. So we have year 2015, megawatt outputs, the values for that year, and then we've got year 2016 megawatt output and the values in that year. Alright, so technically this table is in first normal form, but it is still poorly designed. Essentially this is a report format where it is easy to quickly see the output for each power station for each year. So we can just look at one row for each station and see the outputs in each year. But the problem with this is that the design is cumbersome to maintain because we have to add a column onto the database table for each new year. Also, it's bad design because queries on this table would need to be rewritten each time we add a column to the table. So a much better way of normalizing this table is to do the following. So this is our second attempt at normalizing the data. So instead of having a new attribute for each year's power output, we now have a single column called year, and we create a new row for the power output from each power station for each year. So by putting each output value on a separate row, we are making the table deeper as we have more rows. One tip is to think about how to make a table deeper rather than wider. In other words, more rows and less columns. However, notice that we do have some repeated information in this table. In particular, the station name is repeated for each station ID. This is because station name is functionally dependent on station ID. So what we need to do is we need to have a separate stations table which has all the unique station IDs and station names in it. Essentially, this separate table will hold all the attributes that are in common to each station. So at the moment, this is just station ID and station name. Alright, so let's show that. So here is the fully normalized data structure. We have now taken the station ID and station name and put it into its own table called stations. So this is the parent table. And the original table we've called station outputs, and this is our child table. And the two tables are linked to each other by the station ID attribute. And so the station ID attribute is the foreign key column in the child table. Alright, that's it for this lecture. See you next time. Okay, let's go through second normal form. A table is in second normal form if it is in first normal form and all non-key attributes are functionally dependent on the whole of every candidate key. Okay, let's take a look at a table that is not in second normal form, and then we will go about normalizing it. So here we have a table called supplier parts, and this table has the candidate key, supplier ID, part number. So we have unique combinations of values for these two attributes. If we look at the first row, we can see that supplier ID 101 has a quantity of 250 units for part number 5, and the main city for this supplier is New York. Alright, so this table has some redundancy. For example, every row for supplier ID 101 tells us that the main city for this supplier is New York. And the same thing is happening for the other suppliers. Every row for supplier ID 102 tells us that the main city is London, and for supplier ID 103, this supplier's main city is New York. So we have two suppliers whose main city is New York, and one supplier who is in London. This redundancy is bad, because it means that the table could have some update problems. For example, someone might incorrectly enter a city other than New York for supplier ID 101. If that were to happen, then we would end up with inconsistent data. Okay, so given the assumption that each supplier has one main city, then we have the following functional dependency. Supplier ID functionally determines main city, and this is because each unique value of supplier ID is associated with exactly one unique value for main city. This means that the non-key attribute main city is functionally dependent on just part of a candidate key. This means that the table is not in second normal form. For a table to be in second normal form, all non-key attributes must functionally depend on the whole of every candidate key. This is true for the quantity attribute, but not for the main city attribute. To normalize, we need to remove the non-key attributes that are dependent on the whole of every candidate key. Then we create another table with these attributes and the part of the candidate key on which they depend. So in this case, we are going to take the non-key attribute main city, and then we'll also take supplier ID, which is the part of the candidate key that it depends on, and we put these into a lookup table, i.e. a parent table. Alright, let's show that. So now we have supplier ID and main city in a parent table called supplier main cities. And we can put a primary key constraint on the supplier ID column in this table. If we had other attributes that were applicable to each supplier, then we would add these to this parent table. So that would be things like supplier name, supplier contact details, etc. On the right hand side we have the table supplier parts, and this is the same as before, except now we have removed that main city attribute from this table. So now all non-key attributes depend on the whole of every candidate key. Here we just have one non-key attribute, which is quantity, and quantity is functionally dependent on the whole of the candidate key. So it's dependent on both supplier ID and part number. In other words, quantity is specific to both these attributes that make up this particular candidate key. Also, we can put a composite primary key constraint on this candidate key, and we can put a foreign key constraint on just the supplier ID column, and this references back to the supplier ID column in the parent table. This foreign key maintains data integrity by ensuring that we can only add supplier ID values to the supplier parts child table if they first exist as valid values in the parent table. Alright, that's it for this lecture on second normal form. See you next time. Welcome to the lecture on third normal form. Alright, let's get straight into it. A table is in third normal form if it is in second normal form and no non-key attributes depend on an attribute or attributes that is not a superkey. Recall that a superkey is just an attribute or a set of attributes that has unique values. So let's say we have the functional dependency A functionally determines B. Then if B is a non-key attribute, in other words if B is not a candidate key, nor is it part of a candidate key, then A would need to be a superkey. If this holds true for all the functional dependencies in a table, then the table meets third normal form. Okay, let's take a look at a table that is in second normal form, but not in third normal form, and then we will go about normalizing it. Okay, so here we have a table called suppliers, and in this table, supplier ID is a candidate key. It's also a superkey, as all superkeys are candidate keys, but not every candidate key is a superkey. Okay, so because supplier ID is a candidate key, this means that it functionally determines all the other attributes in the table. Now notice that this table has a functional dependency where main city functionally determines distance rank. So this distance rank column here might be the distance from an organization's warehouse to a city where the supplier is based. Okay, so given that this functional dependency holds true, then this means that each unique value for main city is associated with exactly one value for distance rank. And just to go over a bit more terminology, for any functional dependency, the attribute or attributes on the left hand side of this functional dependency arrow, so main city is on the left hand side, this is referred to as the determining attribute, also called the determinant. And the attribute that it determines, this is referred to as the dependent attribute. So on the right hand side we have the dependent, in this case it's distance rank, as distance rank depends on main city. And we can see this if we look at the data. We can see that when main city is New York, then distance rank is always going to be the value near. When main city is London, then distance rank is always going to be the value medium. And when main city is New Delhi, distance rank will always be the value far. Okay, so is this table in second normal form? You might want to pause the video now and have a think about that. Alright, so yes, this table meets second normal form because all non-key attributes are functionally dependent on the whole of every candidate key. In other words, we don't have any multi-column candidate keys where a non-key attribute is dependent on only part of a candidate key. However, we can see that this table has redundancy in it, so it clearly still has problems, and this is because this table is not in third normal form, because the non-key attribute main city functionally determines distance rank. In other words, distance rank is dependent on a non-key column, main city, which is not a superkey, i.e. main city does not have unique values. And it's worth noting that in some textbooks, they will define third normal form as a table that does not have transitive dependencies. A transitive dependency is simply an indirect relationship where, for example, you might have A functionally determines B and B functionally determines C. Therefore, we can say that C is transitively dependent on A. If we relate it to this example here, then we have the transitive dependency where supplier ID functionally determines main city, and main city functionally determines distance rank. Therefore, distance rank is transitively dependent on supplier ID. Okay, so this table is not in third normal form, and we have the problem of repeated information, which is vulnerable to update anomalies, etc. So how do we go about normalizing a table that is not in third normal form? Well, what we need to do is remove the non-key attributes that are dependent on an attribute that is not a candidate key nor part of one. Then we create another table with this attribute or attributes and the attribute on which it depends. So in this case, we're going to take main city and the dependent attribute distance rank, and we will put these into another table. However, we will also keep main city in this table, and this will be our foreign key. Alright, so now we have created a new table called supplier cities, and we have unique values for main city, and we also have the distance rank for each city. Then if we go across to the right, we can see we have our suppliers table, and this is our original table, and you can see that we no longer have the distance rank dependent attribute in this table. But we still have the main city attribute, and we've made this a foreign key, referencing back to the main city column in the supplier cities parent table. However, there is still a problem with this structure. You might want to pause the video for a moment and have a think about what is wrong with this. Okay, so the problem with this is that in the future, we might get two suppliers from two different cities, but these cities happen to have the same name. For example, there are two cities named Melbourne in the world. There is one Melbourne in Australia and one Melbourne in America. So this is one reason why it's not a good idea to use main city as the primary key in the parent table. Instead, it is better to add on a surrogate key, which we can call something like main city ID. Okay, let's do that. Okay, so now in the supplier cities table, we have added on a surrogate key called main city ID, which is an integer column, and we have set this as the primary key so that it is guaranteed to always have unique values. And in the suppliers child table on the right, we have replaced main city with main city ID, and this is our foreign key, which references back to the primary key of the parent table, main city ID. So in other words, this foreign key here on the main city ID column in the suppliers table, this ensures that we can only add ID values that first exist in the main city parent table. If we wanted to get the attributes from both tables in one query result, then we can do so in SQL by joining these two tables together based on the main city column in each table. Okay, that's it for this lecture on third normal form. See you next time. Hello and welcome to the Boyce Codd Normal Form lecture. Okay, let's get started. Boyce Codd Normal Form is also known as 3.5 Normal Form, as it is a stricter version of third normal form. If a table is in Boyce Codd Normal Form, then it is also in first, second and third normal form. In other words, Boyce Codd Normal Form is a level above third normal form in the normalization hierarchy. And Boyce Codd Normal Form is really important, and in fact it's more important than both second and third normal form. In the words of database specialist Chris Date, both second normal form and third normal form are mainly of historical interest. They're both regarded at best as stepping stones on the way to Boyce Codd Normal Form, which is of much more pragmatic as well as theoretical interest. Even though second normal form and third normal form are not as important as Boyce Codd Normal Form, this course still covered them because they are still commonly referred to in the majority of books, articles and university courses on database design. Also, an important note is that most tables that are in third normal form are also in Boyce Codd normal form. In fact, it is rare to find a table that meets third normal form but does not meet Boyce Codd normal form. Although with that being said, we will take a look at a table that is in third normal form but not in Boyce Codd normal form in just a minute. But first, let's define Boyce Codd normal form. A table is in Boyce Codd normal form if for any non-trivial functional dependency, A functionally determines B, then A is a super key. To explain further, a table is in Boyce Codd normal form if each determining attribute or attributes is a super key, i.e. each determining attribute, determinant, has unique values. So recall that a determinant is an attribute or set of attributes on the left-hand side of the functional dependency arrow. For example, if we have A functionally determining B, then we say A is the determinant as it is on the left-hand side of the arrow. To summarize, a table is in Boyce Codd normal form if every determinant has unique values. Okay, let's take a minute to compare third normal form with Boyce Codd normal form. A table meets third normal form if no non-key attributes depend on an attribute or set of attributes that is not a super key. A table meets Boyce Codd normal form if no attribute, either key or non-key, depend on an attribute or set of attributes that is not a super key. In practice, a table that does not have overlapping candidate keys is guaranteed to be in Boyce Codd normal form. Okay, let's take a look at an example of a table that is in third normal form but not in Boyce Codd normal form. Okay, so in this example we have a table of meeting room bookings, and there are two meeting rooms, the Cedar Room and the Maple Room. In this company they have the following business rules. Only employees from the HR and executive departments can book the Cedar Room, whereas only employees from the sales and IT departments can book the Maple Room. This table has two candidate keys, which are the combination of room, start time and end time, and the second candidate key is the combination of department, start time, end time. Note that the combination of only start time and end time is not unique because we can have two different meetings being booked at the same time. So for example, we have 10 AM, 11 AM on two rows, and that's because we have two different rooms being booked at the same time. Okay, with that aside, let's look at the functional dependencies. So the first couple of functional dependencies here are obvious ones because each candidate key functionally determines all the other columns in the table. So we have the candidate key room, start time, end time, functionally determining the department attribute, and we've got the second candidate key, department, start time, end time, functionally determining room. So no surprises there. But there is another functional dependency in this table, which is department functionally determines room. And that's due to the business rule. In other words, each department can only book one meeting room. For instance, the HR department is only allowed to book the Cedar Room. Same goes for the executive department. The sales department can only book the Maple Room, and same is true for the IT department. Therefore, every value of department functionally determines exactly one value of room. Department is on the left-hand side of the functional dependency arrow, and therefore department is our determinant. However, department is not a super key, and therefore this table is not in Boyce Codd normal form. We can see that department is not a super key because it does not have unique values in the table. For example, the HR department is repeated on more than one row for different booking times. At first glance, you might think that this table is not in second normal form because room is dependent on department. Therefore, room is dependent on only part of a candidate key. However, this table is actually in second normal form because all non-key attributes are functionally dependent on the whole of every candidate key. Yes, room is dependent on department, which is only part of a candidate key, but room itself is a key attribute as it is part of the candidate key room, start time, end time, In fact, all the attributes in this table are key, or also known as prime attributes, as they are all part of a candidate key. Because there are no non-key attributes in this table, then this table is in both second normal form and third normal form. However, it is not in Boyce Codd normal form because we have a functional dependency where the determinant is not a superkey. Okay, so what's wrong with this table? Well, for one, it's vulnerable to update anomalies. For example, someone could incorrectly enter a booking for the Cedar Room by the sales department. So this last row shown here is incorrect because it breaks our business rule that the sales team are not allowed to book the Cedar Room. So only members of the HR and the executive department can book the Cedar Room. Okay, let's now remove this incorrect row. We also have the potential for deletion errors. For example, if we didn't have a booking for the IT department, then we wouldn't know they even existed, as there is currently only one booking for the IT department. Alright, let's now normalize this structure so that it conforms to Boyce Codd normal form. To do that, what we are going to do is we are going to take the department and room attributes and put this into another table. We're going to keep the department attribute in this table as well, along with the start time and end time, because it is the determinant in the functional dependency department functionally determines room. Okay, let's have a look at the normalized structure. So now we have our child table on the left here, and we have a new parent table on the right. Recall that the business rule involved assigning each department to exactly one room. Therefore, we can use department as our primary key in the parent table. Typically, we would use a department ID, but in this case, we're just showing the department name. So we have the HR and executive departments sharing the Cedar Room, and we have sales and IT sharing the Maple Room. Moving across to the left-hand side, we have our child table. We have start time, end time, department. Department was the primary key in the parent table, and therefore we use department as the foreign key in the meeting room bookings child table. Okay, so this example is a bit contrived, as in the real world it would be unusual for a company to have a business rule that each department could only be assigned to one meeting room. However, this was done purely to show a situation which might involve further normalization in order to meet Boyce Codd normal form. Alright, that's it for this lecture. See you in the next one.